All right. Good morning, evening, night, everyone. Welcome to day 2 and final day of the DSA workshop 2020. We have another exciting program lined up, and to kick it off, we want to kick it off in high gear by starting with the talk from Professor Elaine, who's a computational epidemiologist from Boston University, and also a board member of Data Science Africa. And she'll be giving us a talk about how to monitor behavioral risk factors using internet search data. If you never attended a talk from Elaine, strap in, this is going to be super exciting. Elaine, over to you.
All right, hi Billy, thank you for the introduction. Thank you everyone, good morning. So as Billy mentioned, I'm going to talk about monitoring behavioral risk factors with internet search data. So a lot of the work I do falls under epidemiology. Some of you already know this, but epidemiology is a study of the patterns of disease, injury, and health, and factors that contribute to these patterns in specific populations. So when we talk about factors, these can include a lot of different things. So everything from housing to transportation to behavioral risk factors like whether you exercise or not, what you eat, whether you smoke, how much alcohol you consume. So these are all factors that can influence your health. And in epidemiology, we tend to focus on specific populations because there are differences across populations. So the kinds of factors that you see in one population are not necessarily the same factors that you would see in another population. Most of the work I do falls under digital epidemiology, and basically that means I tend to focus on things that people put on the internet and things that are produced through mobile phones, so digital data, and try to understand how we can use that for public health surveillance. So if someone has a cold and they're searching for flu symptoms, is that information that can help us with monitoring how the flu is spreading in a particular community. So my work has included data from lots and lots of different sources. These are just some of the examples. We've done a lot of work around crowdsourcing where we've obtained data from mobile tools that have been developed to collect data about symptoms. So an example is Funyayu that was developed here in Boston. And the goal for that was to track flu in the US. Similar systems exist in Europe and other places. And people sign up to report their symptoms. So they get emails or notifications on their phones, and they get to fill out a survey to see whether they have flu symptoms or not. Another example of crowdsourcing is I Was Poisoned. And this one is just a web application where anyone can log in and provide information about their dining experience. So if you went out and you ate at a restaurant and then you got sick, you can write about your experience. Obviously, when you talk about crowdsourcing, you know that the data people provide is not always going to be true, because you can eat in one place and then not see symptoms. If you get infected in that particular place, you might not see symptoms until a day or two later. And so you might blame the wrong place for your symptoms. But the idea for most of the systems is to see if there is suddenly a significant rise in reports. So is there a significant anomaly in the data? So if you're looking at how many people are reporting on a daily basis, do we suddenly see a spike? And then there's also interest in seeing groups of people report. So if you have 5 people go out and eat at a restaurant and they all get sick, then there's a very good chance that they all got infected at that restaurant. Such data is the one that I'm going to focus on today. And we've used data from multiple sources, Baidu, which is the Google of China. We've used a lot of Google data to look at different things. We've also used data from UpToDate, which is a clinician support website. So clinicians can search for information for different health conditions, and that is used a lot in the US, but it's also used in some African countries as well. And then you have social media sites like Twitter and Instagram, and those can be used for looking at people's behaviors as well. So when people tweet about different things or post about different things on the Instagrams, whether it's about food or exercise, we can get information about what is happening in at the individual level, but also at the community level for this different using these different platforms. We also have consumer review data. So when people write reviews about different things, like restaurants, but also about food products or other products that could have safety concerns. And then you have remote sensing data. We've had talks about this in the last several days of DSA. So data, some of this data can come from Google, and we've looked at how that can inform us about the built environment. So if you look at a neighborhood, what kinds of information can you extract from satellite images? And then also looked at how that can inform us around disease surveillance. So if you look at hospital parking lots over time, for example, can we detect changes in how people are using hospitals? And can that provide us information about start of outbreaks like the coronavirus or other infectious disease outbreaks when we don't have information for that? And then lastly, there are news websites. So news websites tend to focus on mining news reports of disease outbreaks and then putting it in one place. So you can go to a website like Health Map and you see what kinds of outbreaks have been reported in your local community. And that can inform you, especially if you're trying to travel to different places. So today I'll mention two papers. One that was published earlier this year and focused on digital platforms and how those could be used for non-communicable diseases surveillance in sub-Saharan Africa. And then the second one, which builds on the first one, focused specifically on how we can monitor behavioral risk factors for current diseases in Africa. So a lot of people are using mobile phones and internet across the continent. According to the ITU, an estimated 268 million people used the internet in 2018 compared to 19 million in 2005. And there are about 260 million active social media users. So these are people who are constantly producing information, whether it's location information or information about your thoughts, about your feelings on different topics that can inform public health interventions, but can also inform public health policy as well. So on the other hand, we have about 126 million people are projected to have hypertension in sub-Saharan Africa in 2025. About 49 million people projected to have diabetes will have diabetes in 2030. And the most significant part is that currently a lot of cases are not diagnosed. So people who have diabetes do not know that they actually have diabetes, and that can be very, very deadly when you think about the impact on the individual's health. And the reason why we're seeing this increase in chronic diseases, so a lot of these diseases used to be diseases that you see in the Western world, the developed countries, is because we're starting to adopt some of those risk factors that lead to those diseases. So insufficient exercise as more people take vehicles to move around, whether it's in cities or rural areas, unhealthy diets. So if you go to some cities that years ago didn't have any fast food restaurants, now you see fast food restaurants everywhere, and people consider it as something special, and so might consume more of these fatty and salty foods, which are not good for them. And then you have tobacco use as well and excessive alcohol consumption. These are all behavioral risk factors that are quite easy to change to prevent disease, but they're also the factors that can lead to significant burden of diabetes and hypertension and heart disease, and also lead to death. Another reason why we're seeing some of this increase is also because of the growth in urban areas. So Africa is, in terms of growth in urbanization, is the fastest growing continent. And when you start looking at cities, there are differences across cities, but there are also differences within cities. So different neighborhoods in different cities will have different health outcomes because people have access to different resources. So in some neighborhoods, you might have people having access to more facilities to exercise. They might have more access to green spaces that they can actually go out and walk. But in other places, people might not have access to those things. And then there are also issues around access to healthcare infrastructure. And these all fit into physical environment, social environment, access to health and social services. And when we think about the physical environment, we're usually talking about the things that are around you. So what do you have in your physical, wherever you live in, wherever you work, that you have access to that can help or might have negative impacts on your health? And then social environment is usually around relationships. So who do you have relationships with, and how do those relationships help to either improve your health or have negative impacts on your health? So when we think about interventions, there's a lot of discussions about what can be done now to make sure that all these projections about diabetes and hypertension across sub-Saharan Africa do not become true. We think about developing interventions that are both physical and digital, because a lot of young people are online, they're using Facebook, they're using Instagram, they're using all these different platforms. How do we take advantage of these digital platforms to create interventions now instead of waiting until we start seeing, millions of people affected by these conditions? How do we create interventions now that can have impact and limit the number of people that get affected? So there are three ways digital data can be useful, I think. One is monitor health seeking, information seeking. So what are people searching for when they go online? What are people posting when they're on Instagram, on Facebook? What are some behavioral characteristics that we can capture for, especially for younger people who are using these platforms, that can inform us about what they understand about chronic diseases and what they do not understand about chronic diseases. We can also monitor behavioral risk factors. So if people are engaging in excessive alcohol consumption and they're posting that on social media sites, if people are having unhealthy diets and they're posting this on social media sites, we can capture that at the individual level, but we can also construct city or community level indicators that can tell us what is happening in a city, what is happening in the community, and then use that information to start thinking about interventions. And this also relates to the third point, which is misinformation about behavioral risk factors. So people are not just seeking information about food, but they're also seeking information about how to lose weight, how to be healthy. And some of the information you have on the internet, if you've ever searched for these things, are really bad. So how do we identify health misinformation on different platforms and use that as a way for public health institutions to create better information that people can have access to better educate people about chronic diseases? So for this particular study, we've been looking at obesity. Obesity is a major risk factor. So being overweight and being obese is a major risk factors for all the diseases that I have talked about. So hypertension, diabetes, cardiovascular disease. And so starting to monitor obesity or monitor how people think about food and exercise and all those things could be really informative for how we intervene and reduce the prevalence of chronic diseases. So if you look on the figure on figure A, you see that a lot of the highest prevalence for overweight is mostly in the southern region of Africa and the northern region of Africa. But if you start looking over time, you would see that it's been changing significantly across the entire continent. So places that used to have very, very low prevalence are now starting to see higher prevalence. And then again, on B, that's obesity prevalence. You see similar trends where you have higher prevalence in Southern Africa and higher prevalence in Northern African countries. And there's so many factors that also lead to this in terms of culture and society. So in some cultures, being overweight is considered a sign of fertility, a sign of beauty. It also indicates that you have wealth. And so these are all factors that can be very challenging to address. So for our study, we collected data on 100 plus search terms. So we started with cardiovascular disease, diabetes, obesity, hypertension, and we just looked on Google for data for those terms, and then we looked at what was correlated with those terms. So what are the things were people searching for that had similar trends when you compare to searches for obesity or searches for diabetes, and then came up with the rest of the terms that we have. So we have things like, when you look at questions on weight loss and obesity, you have things like, how many calories should I eat to lose weight? How can I lose weight fast? How can I lose weight? That repeats itself, sorry. How to get rid of belly fat? And then when you start looking at exercise, diet, and obesity, you have examples like exercise program, weight loss, exercise program, fasting for weight loss, belly fat burning, treadmill, gym, diet, etc. So we looked at these for 52 African countries because we only had obesity data for 52 countries and not for all the countries. And we looked at how searches have changed over time for all the different countries. And when you look at the countries that have the highest obesity prevalence, you can see that some of the searches have been, they're very different for those different countries. There's so many reasons that could be. Some of it could be language. Countries like Libya, we maybe should be using different language to search for. But a lot of the research that has come out from Africa around social media shows that people tend to use English when they're online. So if you look at South Africa, for example, searches of food and weight seems to be, food and fat seems to be increasing, while weight seems to be going down a little. You look at Tunisia, you have increases for searches for food and fat, and weight is also going up as well. So these trends can be important, especially when you start thinking, so food captures a lot, fat captures a lot, weight captures a lot, but when you start thinking about specific terms or specific phrases like, how do I lose weight, or what does a healthy diet look like, or should I fast to lose weight? So that could capture specific trends in how people are either seeking information and how that information seeking is changing over time. So when we looked between the terms that we had, so we had 100 plus terms, which ones were most correlated? Some of the ones on this page are kind of almost a repetition of each other. So you have like diet and weight that is significantly correlated, but you also have food and weight being significantly correlated, how to lose weight, and green tea. It seems like people think green tea is very good for weight loss. So you see searches around that. Gym and weight loss. So the underlying idea is similar in that if someone wants to lose weight, then they might be trying to find gyms in your city, or they might be finding specific things that they should be eating to lose weight. We also looked at terms that were correlated with prevalence of obesity and overweight. And we had things like obesity treatment, weight loss shakes, which I think is a big thing in some countries. Excuse me, diet plan to lose weight, weight loss supplements, diet plan, and gym. So those are some of the top searches that were significantly correlated with obesity and overweight across the continent. So the next step, what we did was fit a bunch of regression models. So we selected models that were tree-based, models that were more of a least squares approach, and then models that were kernel-based. So support vector machine is an example of that. And I have the figure over there to the right, where in support vector machine, you're trying to find the hyperplane that maximizes the separation between your classes. And your classes are not always linear, so you can use autokernels to capture the separation between the two classes. And then you have random forests and boosted regression trees, which are both tree-based methods. So these are very like simple machine learning approaches that a lot of people just run. There's nothing complicated in them. But I really like starting with simple methods because sometimes they get the job done well, and it's easy to explain these methods to people who might need to understand it. And then if these methods don't work, then I can start thinking about more complicated methods. But going simple is my approach in life. So these are the results that we have. So at the top, you have the model that's been fed, and then at the bottom, you have the predictions that we're making. So we divided our data into two sets, so a training set and a testing set. And then we use the training for the feeding and then the testing for basically estimating what our models will predict. So you have the ensemble model. The ensemble model combines random forests and boosted regression trees in this case. So you have the individual model predictions, and then you have the combined prediction in the ensemble model. Similarly so at the top is the feed. So you have the feeded model separately and then predicted, and then combined feeded, and then you have predictions similarly as well. And our model seems to do very well in some cases, not very well in others. So if you look at the ensemble model, which performed best compared to the individual models, you see that there's some overestimation, no, mostly underestimation. So if you look at obesity prevalence for the ensemble model FEAT, you have obesity prevalence being around 30 for some countries, and that's being underestimated as between 10 and 15. And so those are things that we're working on to try to understand why we're getting those underestimation. And then when you look at overweight prevalence, you also see something similar, but actually the models seem to do a bit better for overweight. Actually, I didn't really trust the model outputs for this because they were too good. I think our correlation between the model estimations or other sample predictions and actual data was about 0.9 something plus percent, like 0.98 or so, which I thought was super high. So trying to figure out why that's the case. So some of the challenges that we have thinking about how digital data can be useful for public health surveillance in Africa include a shortage of high quality surveillance data. So you can actually think of this as an opportunity. So if we don't have really good surveillance data, maybe digital data sources can fill some of those gaps. And in some cases, they can, depending on the question you're asking. But for standard surveillance approaches, we need data that has been validated. We need people to be tested for diseases and actually have confirmation of disease. So we can't completely use digital data to fill in those gaps. So digital data can only be a supplement if we're trying to understand things like behavior. It could be useful in those cases, but when we actually need numbers, then we need better surveillance data. We also have cultural influences, as I mentioned, that are very unique in how people think about health, how people discuss health. And these are all things that we need to take into account when we think about chronic diseases. And then there's socioeconomic inequalities and representation. So who is being captured in this data? Who are the people that are actually searching for this information? My fear is that we might end up developing interventions that only target people who are already in higher income groups, people already have access to the information that they need, and that would leave out the individuals who are in poor categories and do not have access to some of this information. And so it's very important to think about representation and how the systems can be used to improve health across the entire population rather than just for specific people. And then obviously the ethical challenges with individuals understanding how their data is being used, how what they're putting online can be used for good and for bad. And to address these challenges, we proposed locally developed and contextualized strategies, the work that most of you are doing around digital literacy education, so helping people understand how the digital platforms you're using are collecting information on them and how that information is being used. Design of appropriate consent systems, so having people actually opt in into studies or opt out of studies, and methods that address a lack of demographic representation. So always thinking about representing everyone and making sure that the tools we're developing are benefiting people across the entire population and not just people in higher income groups. So that's all I have. I want to acknowledge people who've contributed to this project. Lots of people at Boston University, and then we have David Singer from Sierra Leone. So thank you.
Thank you, Elaine, for that wonderful presentation. We have time for questions, actually a lot of time. Feel free to use the chat or the Q&A or raise your hand if you want to speak. While people are still gathering the questions, I have one question to start us off. So back to the predictions, especially the ones that are under predicting and over predicting. I was wondering, I know you say you're starting with simpler models. I was wondering, is there a way to use something that gives a little bit of uncertainty estimates or confidence intervals? So you can get confidence intervals even on this linear style predictor side, so that the prediction itself also is qualified by some range, and maybe that can better understand.
Yeah. So I actually had that in some version of this, but not in this plots. But yes, I think confidence intervals are very important. And there are ways to estimate confidence intervals with random forest and other machine learning approaches that we can use.
Cool. Any other questions? Don't be shy.
There is another question in the chat.
Yes, there's a question here which asks, have you shared your findings with any health authorities in Africa? Part 1 and part 2, what was their reaction?
No, we haven't. So the project is still ongoing. Hopefully when we finish it, we will be able to share with individuals in Africa and health authorities and get some feedback on that. I think people are still sleepy like me.
Saturday morning.
Yes.
Somebody in the chat says, great talk, Elaine.
Thank you, Colin. I think someone is raising their hand. Then took it.
Yeah, I thought I saw it for a second too, but it disappeared. All right, there's a question on the chat. Was all this based on Twitter data?
No, this was based on Google searches. So what are people searching for? What particular terms and phrases are people searching for?
I guess a related question to that would be, how do people get access to this Google search data if somebody wanted to look into this?
Yeah, so Google data is publicly available through trends.google.org. Was it .com, google.com. So you can collect that data at the country level, but you can also collect it at the regional level. So if you go to the website and you search for a particular term, you can select the country that you're interested in and then scroll down And then you'll usually have a map showing you where the searches are coming from. And on that map, you can click what regions you want extra data for, and that would show you the data for those regions.
Cool.
But you can
There's
also...
It's an anonymous question on the Q&A, which is asking, have you done any analysis to establish which digital sources are most likely to show more valid data, e.g. social media versus crowdsourcing?
We haven't done analysis comparing data sources, but we've looked at analysis on how different data sources can support each other. So the information that people put on social media websites, for example, like Twitter, is different from what you will see on Google. So what we see on Google is a lot of general topics, but also topics that are very private, because people feel that it's a protected space in a sense. They're not sharing the information with the whole world, so people can search for a lot of different things. But on spaces like Twitter and Facebook, people tend to post things that they feel more comfortable with. And so these different data sources can help each other in filling gaps that exist in individual sources. And we've used that for things like influencer surveillance to develop models that take into account all of those different data sources together and see if that produce better estimates of influenza like illnesses in different communities.
Any other questions? Somebody's asking, can you please go over this result again? I'm assuming by this result you mean this slide being shown?
Yeah, I could do that. So what we did for this analysis is we have a data set that has obesity prevalence for every single country that we have. And this is over several years. So let me go back to that slide. Sorry. So this is from 2010 to 2016, and this is all 52 countries. And then we split that data into two sets. So we have a training set and a testing set. And then for our models, we use the training set for the fitting, and then use the testing set for what we label as predictions. And each of the models that we consider, so like random forest and BRT, which is boosted regression trees, we feed separate models, but then we also have an ensemble model that is fitted combining predictions from these separate models. And so what you're seeing on these slides is what the separate models are doing and then what the ensemble model is doing. And in all cases, the ensemble model does better than the individual models.
And somebody's asking, different person, how do you distinguish people doing searches for research purposes rather than performing search because they have that condition?
Yeah, that's something that we can't distinguish. So Google has a couple of studies that they've done where they actually try to look at what people search for first, and then search for second, and search for third, and then use that as a way to determine whether they're just looking for research purposes or if they're actually searching because they have a condition or experience particular symptoms. So they can do that, but we can't do it on this end. What we only see is aggregated searches. And so we focus on it more as interest in that particular area. So if someone is searching for something, whether it's for research or for individual purposes, there's something happening in that community to make them do those searches. There's something in perception. So if we go back maybe 5 years before, we might not see the same level of interest, but if that interest has changed over time, that could tell us that there's something changing in those communities.
Any additional questions? We still have a few more minutes.
More minutes.
Well, there's another question. The question is, what do you hope the final product from all this work will look like? Like a product that you want to pass on?
So our initial product, which is what I'm showing you on the screen, is basically trying to understand whether this data can be useful. And then if it's useful, the next step is how do we get data from other sources? So how does information from Instagram, for example, so we've looked at what people post about for foods in Kenya, for example, how can that information be used in combination with this to support how we think about interventions and design interventions for specific communities across Africa. So ideally, if we can have some of these companies who collect this data collaborate with us, then we'll have better information than just the total number of searches. We can have also more granular information as well. And that can help us with designing interventions, whether it's creating ads for some of those websites where you teach people about these chronic diseases, or it's creating specific tools, whether it's apps that people can use to learn about the diseases, or community interventions, like what are other ways that we can reach people beyond digital platforms.
All right, there's another, so there's two more questions. So I'll start with the Seko's question. It says, is it possible to combine this type of study with in-depth surveys? And what might that lead to which existing today? What might that lead to which doesn't exist today in your findings?
So it could lead to, I think I can answer both questions in a sense. So it could lead to validation of some of these findings. So I know some colleagues who did something similar looking at the flu, where they got people's postings on social media and then actually had them get their medical records as well to see if there is validation, if people are just posting random stuff about symptoms or if they actually had the flu. And so going that extra step of doing survey information can give us a sort of validation. The challenging thing with surveys is that they tend to be a one time stamp of someone's behavior. So you're not seeing how this is changing over time. But if we had like individual level data from social media, for example, you can see how people are discussing different topics and how that is changing over time. So that gives us more detailed and a more rich understanding. And we're also not really dealing with things like responder bias, which you might see in social media, in surveys where they think you might be judging them and so might answer questions differently. So there are some ways in which survey data can be useful when we combine it with this, but there are other ways that it might not be very useful because of some of the biases that come with that data set as well. So the other question was around validation. So if we're just talking about model validation, what we're doing here is fitting a model using a separate data set and then trying to predict using it a separate portion of the data that was not used in the fitting. But in terms of actually validating whether someone's searching for how to lose weight is actually obese is something that we can't do because we only have counts of how many people are searching for those things.
So let's take in maybe 1-2 more questions. In the meantime, Hallelujah, be ready.
I'm ready. I'm ready.
Any final 1 or 2 questions before we switch presentations? I guess there's not. If there's any questions later, you can always reach out to Elaine that via DSA, or Elaine, if it's okay with you, you can share contacts that people can reach you with. All
yes.
right.
Email right there on the screen, or you can find me on LinkedIn. Sometimes I'm on Twitter, less these days, but that could be another option.
Thank you. All right.
Right.
We'll proceed to the next talk. So now that we know that people are eating too much and being overweight, which means some people are eating more of the food that we need to spread to everyone else, let's hear from Hallelujah about how we can increase agricultural productivity in Africa to generate this extra food.
Please, can you enable me to share my screen? Hello?
Go ahead now.
All right, thank you. Yeah, can you see my screen now?
Yes.
Oh, all right.
Yeah,
Thank
you
you.
also can start the presentation.
Yes. Good morning, everyone. It's about 6:55 a.m. here in Nigeria, and I'm making presentation on an ongoing project, which is increasing agricultural productivity in Africa using discriminative deep learning models for farmland bird invasion and identification and dispersal system. It's a project currently being carried out at Bowen University, Iwoya in Nigeria, and it's a joint effort of about 4 of researchers. We are making a presentation here at Data Science Africa Summer School and Machine Learning Workshop. Thank you. Yeah.
You go to slideshow so that we can see it better.
Okay. Is it better now?
Yes, thank you.
All right, thank you. So what's the motivation behind our work, or what's inspired us to go into this work? In a research, it's been predicted that by 2050, the farmland in African countries would have been doubled the current size of farmland. Well, however, with this prediction, it's been observed that due attention has not been given enough to farming intensities and regime on bird communities. And that's part of the reasons why we feel, okay, let's delve into researching in that area. Equally, it's been observed that damage caused by birds across the globe is numerous, expensive, and it varies, although most of the time they are similar from continent to continent. And here in Nigeria, to be precise, bird scaring in the agricultural sector is still predominantly manual, and we feel there is need for a change in narrative or a change in approach for us to really get rid of all these damaging devices or all these damaging animals on our farmland to increase agricultural productivity. You can see on my next slide about 4 different frames where manual approach are being used as scarecrow for birds on most Nigerian farms. The first frame is showing a farmer trying to scare birds off the farmland, a rice farm to be precise, using his arrow to get them off. While the second one is using stick to chase birds away or to disperse birds on farmland. And the fourth one is using like a scarecrow that is presenting the physique of a man to present the presence of someone on the farmland and then to scare birds off the farmland. The same applies to the fourth frame. And what we have observed is that most times these birds get familiar with this approach and it doesn't really get effective as expected. In fact, in recent time, most farms are already adopting solar farming system, but enough attention has not been given to scaring or dispersing birds off our farmland, particularly in Nigeria. And we feel this an area that we really need to pay attention to if agricultural productivity will truly increase and we have maximum yield on our farmland. What are the implications of farm or bird invasion on farmland? One, as farm produce gets higher, the threat of bird damage on this crop increases as well. And when they damage our fruit or our farmland, it attracts more insects, which contribute to spread of diseases on farmland. With this, profit degradation setting and food shortage is experienced. In fact, it has been discovered by scientific proofs that bird droppings, that is their poo, can constitute some major health issues such as salmonella, which causes diarrhea and vomiting, then flu-like illness like psittacosis, which is a flu-like illness in its own case. Then farmers have majorly been adopting manual precautionary approach, just as I showed in the previous slide. So in essence, we feel there is need for a disruptive technology to be put in place in order for us to change the narrative if our agricultural production rate will increase on the continent of Africa and Nigeria, to be precise. Some authors have been able to work on issues pertaining to bird invasion and the impact they have on farmland. Like Brian and Bumford predicted, or they asserted that the rate of damage that bird cause on farmland is enormous, and it makes US fruit growers even to lose hundreds of millions on farmland. That's talking about the impact of bird invasion on farmland. And going downward the stream, a number of authors equally asserted the importance of putting in place automatic scarecrow in order to mitigate the effects of bird invasion on farmland and to increase agricultural yield. That's the essence of other authors that worked in that line. So in essence, they all asserted the importance of automating the process of scaring and dispersing birds on our farmland. This our own model or our own architectural design that we try to put up to get or to disperse birds off farmland. We ensure that camera is stationed at different points on the farmland to detect the presence of birds on farmland. And not only that, the camera is working real time, which is meant to capture a live stream, and the live stream is broken into different frames, which are images from the video that has been recorded. And then there is image processing, which is done on the frames that have been captured for feature extractions. And then it is passed into the model for detection and for identification. We use the model to produce the image with bounding boxes, as you can see on image acquisition object detected section, which is the pre-processing step of the framework. And when the image is subtraction to differentiate between the background and the particular image that has been captured, then feature extraction is done and then stored into the database. And then for scaring the sound, scary, so we are not just using one particular sound, but a single sound. The birds get be of little or no effect on. So we employ different scary sound on the farmland. It triggers it off the farmland. And by this, we mitigate the effects of bird invasion on our farmland. In this work, we were able to download some data sets from an open source, open image data set online. And there we were able to get 4,000 images in which we made use of 3,000 for training and 1,000 images for our test set. In the work, we made use of 3 different algorithms to see the most effective of them. We made use of RetinaNet, we made use of YOLO, and then faster RCNA. And Python libraries, that is TensorFlow and OpenCV, were used for our work. These are the results that we're able to get from the 3 different algorithms at 4 different thresholds, that is 0.20, 0.30, and 0.40 and 0.50. Those are the thresholds we use. And then for the 3 different algorithms that we employ, that is RetinaNet, YOLO, and then faster RCNA. And from our discovery, we discovered that in terms of accuracy, faster RCNN produced the most accurate results, while in terms of recognition, YOLO tends to be the fastest in terms of identification and recognition of bird images on farmland. We're able to validate our results using ANOVA, and this is the outcome, or this is the results that we're able to get from our validation as shown on the screen. By implication, the validation revealed that faster RCNN has the highest accuracy with over 85%, followed by RetinaNet with 75% and YOLO by 70%. And in terms of recognition accuracy, YOLO outshined the 2 other algorithms in terms of recognition time, as shown in the previous figure. And in conclusion, the work provides an automatic and faster approach to pest bird prevention and dispersal on farmland. And we hope that with this approach, farmers will not need to be on site every time to scare birds off, either by using their stick to chase them away or bows and arrow to get rid of birds. But beyond that, they are going to have cameras placed on farm and sounds, corresponding sound, to get rid of these birds and to increase agricultural productivity in Nigeria exponentially. These are some of the references. Thank you.
Thank you very much. We have time for questions. Please use the chat function or the Q&A or raise your hand. While people are gathering the questions, I have one question.
All right.
So you said you use YOLO version 3, the one based on the darknet architecture. Can you shed some light on the type of compute that you used? Was this all on some embedded chipset, or what kind of computer did you use to get this result?
I don't get your question, please. Can you?
The question is, what computer how powerful was the computer you used to generate these results? And
you know, in this case, we made use of Colab to get our work done.
Okay, in that case, what's the plan for deployment? How do you bring this to the field? What kind of computer are you planning to use to deploy this in the farm?
Yeah, currently we have been able to do a model in the lab, and we plan making use of GPU-based system for our deployment. And then, am I answering your question?
Yes.
Yeah, we intend making use of GPU-based high-ended system for deployment on our farmland. Basically, the camera will be positioned on the farmland to detect, and then it will actuate the sound for scaring birds off the farmland. So that's what we intend doing.
Thank you.
Yeah.
There are two more questions for you. So the first one says, good morning, nice talk. Is the accuracy at the task of bad, no bad, or on the task of identifying the type of bad which is present?
It's bird or no bird. Yeah, that's what is the accuracy is basically meant on bird or no bird. We are not yet delving into the various type of bird. Maybe it's an eagle or a koala or whatever. But the moment it cites the image of a bird or a flying object majorly, it triggers the actuator to act.
Thank you. The second question on the Q&A is, can drones also be used to scare and or monitor?
Drones can majorly be used to monitor, but I feel it may not, because with time, these birds are getting more intelligent and they get familiar with objects on farm. So the moment they are familiar with the drone, they may not, it may not be as effective. So majorly we can use it for monitoring, but when they get familiar with it, it may have little or no effects. Different scary sound on the farmland. So majorly we can use drones for monitoring, and then it reports back to the base station.
Thank you. Another question for you from Ernest is, if the task is bad, no bad, why use object detection? Wouldn't it be easier to use a basic CNN convolutional neural network?
We'll look into that. I think that's an idea that we can really further delve into to check. It's still a work in progress. We are only reporting what we've done so far. So we'll look into that, maybe making use of CNN for object detection.
Maybe Ernest can clarify that later, but in the meantime,
okay.
Another question for you is there any hardware and software tools you have used to do it rather than camera?
Not yet. Not yet. We, just as I said, majorly at this point, we only worked on the model right in the lab. We are yet to deploy it on farmland. And we got our data sets from an open source data set repository online.
Thank you.
Yes.
So there's another question. Ernest, can you clarify your question first before I go to the next one?
I just did. I was wondering whether you could use a basic classification model instead of doing object detection.
All right. Thank you, sir.
And now, okay, the next question is, so my issue is some farmers have power failures and I think cameras needed. How will you handle it?
Okay, in our own case, we are trying to ensure that we have various backups. And then, Nigeria, one of the major problems we have is power supply. We do not intend depending on the power supply from national grid. We want it to be solar powered, such that the power supply will always be available, and then there will equally be some battery backups for it. So the issue of power supply will be handled using solar power energy.
Okay, we'll take one more question before we switch to Andrew. So that last question is, are you also seeking to explore the types of noises so that to understand which one works best over time so that there's no issue of habituation?
Definitely. We intend exploring different types of scary sounds such that the birds will not get familiar with a particular type of sound so that it won't lose its efficiency.
Thank you. We'll move on to the next presentation. If you still have any more questions for you, just put them in the chat. Thank you for the presentation.
Thank you.
All right, next up, we are going to move to Andrew, who is going to tell us about using deep learning to detect brown spot disease in passion fruits. Andrew, you can present whenever you're ready. Andrew? All right, so it seems like Moses is going to present on behalf of Andrew. So Moses, can you go ahead?
Thank you and good morning to you.
Can you share your slides?
I hope that's going to... I hope the slides can be seen.
Yes, we can see them.
Okay, thank you. I'm Moses Pomera. I'll be presenting on behalf of Dr. Andrew. This is work done on brown spot disease detection in passion fruit leaves. It's part of a bigger project that is aimed at building a portable deep learning platform for passion fruit disease identification. I'll give a brief background and then talk about the data set, the model that we used, and the results that we've been able to achieve up to now. So pests and diseases significantly affect farmers' yields through and increase losses that are realized. Like if you lose part of your field, you're definitely going to get a very big loss. So farmers, mostly smallholder farmers, which are the majority, at least in Uganda, they lack sufficient knowledge to combat these challenges and usually depend on field extension workers and experts that do routine visits to the farms to give training on how to deal with some of these challenges, especially disease diagnosis and also just good farming practices. However, these field extension farmers are not able to reach most of the farmers in a timely manner, and for some of these crops that have very short lifespans, by the time the field extension officers reach the farm, it's already too late. So the gap that we noticed was that there was a lack of a reliable, timely diagnostic intervention that could help these farmers. And we sought to fill it by developing a portable platform making use of a deep learning algorithm to do the disease diagnosis. So most of these experts, especially now for passion fruits, use Well, when they go to the farm, they look at the crops, look at the leaves, they look at the fruits, and do the diagnosis. So this seemed like a perfect problem that could be solved using computer vision, which is what we did. So for this particular work, we focused on passion fruits. A brief about passion fruits. They are vine species of the passion flower commonly grown in tropical and subtropical areas. They are popular for their sweet, seedy fruit that is called the passion fruit. In Uganda, there are several varieties that are grown, including the golden fruit or the yellow fruit. There is the hard-shelled passion fruit. Then there is grenadilla, and there is a local purple, which is what you're looking at. So this is a fruit of focus for this work, given that it's the most widely grown around the country and has the most commercial value. So passion fruits are affected by a number of diseases, including kola rot, the woodiness disease, and the brown spot disease. And for this work, we focused on the woodiness virus disease and the brown spot, given they are the most rampant and the most aggressive. So on the left, you have a leaf exhibiting the symptoms of brown spot, where you see the brown patches on the leaf. So brown spot is caused by a fungus, and it affects both the fruits and the leaves of the plant. It's a fungal disease, so it has a cure. It has a chemical control. Then the other disease is the woodiness disease. This is caused by a virus, and the symptoms involve crackling the fruit. As you can see, the middle fruit, it disfigures the fruit, makes it deformed, and causes it, well, the plant just dies. So unfortunately for this virus disease, there is no chemical control. So if it happens to, if a plant gets infected, the only remedy is to destroy the crop. So if it infects the whole field, then the whole field has to be burned down. So timely diagnosis is very important for such diseases, and that's basically what we aim to address with this work. So there wasn't a data set to use for this work. So the first task was to create one that we could use for the data analysis. So we collected about 20,000 images from around the country, that is the central region, the eastern region, and we shall begin to the western region. So the images were captured using regular smartphones, because this is how it's going to eventually be deployed. So it will basically be the same capturing methodology. The collection was done in conjunction with the National Agricultural Research Organization. These people helped us to do the on-field diagnosis. Basically tell you this is a healthy leaf, this is a diseased fruit, and what the disease was. So later on, when we have the full data set, we intend to make it open to the community for whoever needs to do further research in this field. So for the pre-processing, at least for this particular work about brown spot, we selected 2,000 images randomly, then cropped them and resized them to 400 by 400. This was mainly to improve the increase the training time, improve the rate at which we train the model, and also have a bigger batch size. They were annotated using a label box, and we split them according to the rate: 70 for the training, 20% for the validation, and 10% for testing. So given that the model is going to be deployed on a regular mobile phone, we had to consider the efficiency, that is the computational cost of whatever model that we're going to use, and without compromising on accuracy. So this led us to choose the efficient net neural network architecture model that we have used for this work. This is one of the largest state-of-the-art models developed at Google Research. The link is included in the references for those interested, but basically it builds on the efficient net classification model and then adds the novel bidirectional feature pyramid network layer. So for the training, we had to use transfer learning given the number of images that we have. We have quite a small data set. And this particular efficient net3 model was trained on the Cocoa data set. So it gives a fair balance between complexity, as it's computationally, its cost is very low on computation, and it gives a reasonable accuracy. So we use a batch size of 4 and the learning rate of 0.08. Yeah, an optimizer of the stochastic gradient descent with a momentum of 0.9. And we trained using the K80 GPU with the RAM of 56 gigabytes. This was using the Azure cloud service. So we suffer trained for 10,000 epochs, and this is the preliminary results that we have at an AP, or the minimum average precision at the intersection of a union from 0.5 to 0.9. On the validation set, we got 0.32, and on the test set, we got 0.35. So this is an example of an image on which inference was done. We have the ground truth and we have the predictions. This is at the threshold of 0.4 or 40%. So the model did perform well on some images, and in some cases, like this one, it totally failed to identify the brown spot patches. Yeah, so another performance indicator that is important for this project is how much time it takes for the model to do inference. Since we are going to use a phone, we closely related it to the CPU time, which is 0.6 seconds. Much faster than the GPU, but in deployment, we won't have a GPU. So, yes, the model does generalize with an MAP of 0.51. However, as you've noticed, it does not exactly, it's not able to capture all the different disease patches, especially for brown spot. So that is one region that we need to improve on. And then there is comparison that should definitely be done with other models. We intend to do one with the yellow and then the single shot detector. And then we also plan on coming up with a data documentation policy to make it more robust against new data cases that haven't been seen. And certainly we intend to add more data to the pipeline to have the model and all the variability in the data set. This work is funded by the Research and Innovations Grant at McGill University and was done in conjunction with NARO. We had support from NVIDIA that gave us GPUs and label box that allowed us to use the platform for the labeling. It was done with NetLabs, which is a center of excellency in Makerere. We also got a grant from Microsoft that allowed us access to the cloud that we've used that has been very useful, especially in these times. And we've been working in collaboration with the AI Research Lab. Thank you, and I'll take any questions.
Thank you. Any questions? All right, first question coming up. First question is inquiring about your data set. Did you consider the time of the day the images were taken?
Well, not exactly, because we had particular times we would be in the farm, but I believe it's something to consider going forward.
It's another question in the Q&A. So the question is, can you send a photo to do the processing in the cloud, or is it essential to do the processing on the phone?
So it really depends on who is using the platform, because most of the people that we are targeting are in very remote areas where there is no network, there is no cellular network connection, so there would be no connection to the internet. The model has to be on the platform. It has to be on the edge.
Thank you. Another question is, there's some doing work with cassava and you're doing work with passion fruit. Is there a collaboration which you think might help the farmers between your projects?
Sorry, I didn't get that.
So the question is, there's some other people doing work with cassava and you are doing work with passion fruit. Is there a collaboration between yourselves which might help, which you think might help farmers between your projects?
Yeah, well, I think definitely a collaboration would be useful, as passion fruit is just one other plant that could be added to maybe a bigger diagnostics platform, because also the farmers are always moving from maybe one crop to another, so it would be very helpful if someone is going into the passion fruit field. This would be a tool that could definitely be of use to them.
And another question from Ernest says, so will this be deployed for use by farmers? Any considerations for the UI at this time, the user interface?
Yes, we intend to have it deployed as a mobile app, but also, especially for the field extension workers, we intend to have it deployed through another platform that's a Raspberry Pi based platform. They are not conclusive UI considerations, but I would presume it would be a regular application. You have the model in the back end, take the picture, and then you get the disease diagnosis and how to intervene. The next steps, now that you know what the problem is.
Thank you. Another question on the Q&A is asking, what weather conditions, no, it's asking, were weather conditions taken into account when the images were taken?
No, they were not, because, okay, we had defined times to take the pictures, but I think that's one thing that is surely of consideration, and given we're still collecting the data, we shall include it in the later works. But for now, we shall use augmentation techniques to include all this variability.
Thank you. Any other questions? I have one last question. So, I mean, I know this is still early work, but have you considered maybe plugging in some interpretability techniques to help do a little bit more introspection of? So right now we have an AP of something like 0.3. It would be nice to know if the type of failure cases so far that the model is experiencing, and maybe something like saliency maps can help shed light into maybe the model is only failing for certain types of leaves or shade or zoom of the image or something like that.
Yes, surely that will be put into consideration going forward.
Oh, and there's one more question. I guess that's the last one. What evaluation techniques have you used to evaluate your work?
So at this stage, we have only used the mean average precision on the test set.
Good, thank you. Let's thank Moses once more as we switch over to Jason. If you have any further questions, just put them in the chat and Moses or Andrew can answer them. Jason?
Yep, Billy, can you hear me?
Yeah, 1 second. I'll make you co-host. All right, you can present now.
Okay, let me share my screen. Can you see it?
Yes, nice and clear. So Jason is going to talk to us about how to leverage IoT, Internet of Things, and machine learning to improve monitoring of water resources.
Okay, thank you, Billy. I hope my audio is clear too.
Yes.
Okay, thank you. So I'm Jason, Jason Kabi from Center for Data Science and AI, that is Dedan Kimathi University. And I work closely with Shira Maina, who was also part of DSA, who is also part of DSA, that is. And I'm going to take you through leveraging IoT and machine learning for improved monitoring of water resources. And also, that is case study, we are conducting our case study at Upper Wasonyiro River, which is one of the main rivers found in Kenya, that is central Kenya. And also I'm a DSA first timer, so thank you for the opportunity. Okay, now my project aims to develop a water parameters monitoring system for the Wasonyiro catchment. That is, in this case, we are trying to get figures on water level and water flow rate figures also. Wasonyiro has been a lifeline for a lot of communities around it. That is different counties in Kenya. And so to monitor water level in it will be very essential in that to ensure equitable distribution of water. So effective monitoring is very essential because when there is no equitable distribution of that water, then there will be conflict between the water user communities in this case. So the monitoring is essential, and that's why we are monitoring the water level in this case. Also, monitoring will be necessary when sourcing data to quantify unsustainable water usage or destruction of the catchment area. Now, the catchment area of the Wasonyiro is what we are dealing with, and to find data to quantify, sometimes people would say the catchment is destroyed, but you can't quantify it in that. So in this case, we are finding data to quantify the destruction of the catchment area. Also in this case here, we'll be looking into analyzing satellite maps in that to see the amount of deforestation, maybe the amount of encroachment by human activities in this case, which will be leading to destruction of that catchment, that's why we are monitoring the water parameters in this case. Also, our project is also a learning tool for us at Center for Data Science and Artificial Intelligence, as we look forward into sharpening our skills in data science and machine learning in this case. Also, the river is dependent on by wildlife art. This is Olpajeta Conservancy. Olpajeta Conservancy is located in Kenya, and part of the river, quite a large stretch of the river goes through the conservancy. So it will be maybe in their best interest to say that they would like to know the status of the river, because it is part of their ecosystem and there are a lot of beautiful animals there. So it will be there. The data will be vital to the management to know the level of water maybe and the status of the river in this case, because it is part of their ecosystem and it is the only river that crosses the conservancy, and it is dependent on by a lot of wildlife in this case. So in my title, I have two aspects towards the IoT part and the machine learning part. So currently, because it is work in progress, on the IoT, we looked into deployment of the IoT network. In this case, we are using the roller network to collect our data. Also, deployment of the prototypes that is part of the IoT, and also setting up simple web infrastructure to handle data transfer and the data visualization, sorry, in this case. Also, on the machine learning part, currently we are tackling anomaly detection. I think we had a very nice and extensive lecture on that from Tom Dietrich, I think from Oregon, on anomaly detection on time series data from TAMO. So as we are looking into anomaly detection and also creation of prediction models, which we are looking forward to, but currently we are working on the anomaly detection for our system in this case. So the IoT, the prototype we have it uses a ultrasonic sensor in this case to collect the data, and a multi-tech M.dot. A multi-tech M.dot is a very, very small microcontroller that is roller enabled, that is able to connect to the network or to the gateway in this case here, then to a cloud platform where we are able to collect the data. From that, we are able to transfer the data to a GCP, that is Google Cloud Platform database, and from where we are able to visualize the data, we are able to do all this machine learning stuff on it from the database in this case. And now I talked about the Olpajeta Conservancy. That is where we are working, and we are looking into deploying sensors around this stretch of the river that's running from this boundary, the southern boundary here, to the northern boundary here. Recently, they set up a tech lab at the Conservancy so that interested parties and interested in individuals and institutions can maybe deploy conservation technology in the Conservancy. So that has been a very huge help for us from the tech lab at the Olpajeta Conservancy. This is the Eastern Region. So we are looking to deploy sensors from the upper border here to the southern border so that we can monitor it. That is the water level sensors and also the flow rate sensors in this case. From there, this is one of our prototypes here. You can see the sensor here. This is a cage. maybe to get clear, this is the cage here to protect it from damage. This is it at the deployment site. This is it at the lab. We are testing whether it is measuring. It was quite nice at the lab. So this is it at deployment here from the water. So we are measuring the height from this from the water level, from the water service here to the sensor. So originally we had to measure the height itself from where physically from where the sensor is to the water service, so that we can compare with what we are getting from the sensor, and it was quite nice. We are getting very good results from it. Also, the first prototype, as you can see, this is a cage here. It's protected. The first prototype was strapped on the bridge here. We managed to strap in on the bridge here, but like I said on Thursday, baboons descended on it and it didn't last a week. So what we did is we designed a cage that we decided to design a cage and put it inside there so that we can protect it from the primates there, the baboons and the monkeys there. So the cage is not part of the prototype. You can just remove the prototype itself and leave the cage there. You can replace it with another. So because we saw if we make the cage part of the prototype, it will be quite hectic, removing it and replacing it with another one. So we just decided the cage should not be the part of the prototype in this case. And the prototype now, we deployed it back in April, and we have been collecting data since. Okay, to visualize the data from the single, currently we only have that one sensor. It is a test run before we deploy others to see how it behaves in the environment. So currently we are collecting data from it, and we managed to set up a dashboard to visualize the data. If I was to manage to set up a dashboard to visualize the data in this case, was to transfer it here from the dashboard. This is the dashboard here. From here we are collecting the real-time data here. As you can see, here we have data that is very correct, maybe during the day here. We also have data on the same level. We also have anomalies on the upper side and also anomalies on the lower side. The time zone is Africa, Nairobi. So today is August 1st. I think we have some data in from 8:27, that is 9:27. So we have intervals of 30 minutes from the sensor. So we are collecting data from it there. This is the real-time data from the sensor. Here you can just adjust the date and you can get the data. Because you can see you have data from the same level here. Most of the data is at the same level. Then you have anomalies on the upper side. And also you have anomalies on the lower side. This was July. If we go to June, maybe a couple of days on June, also you can see that we have anomalies upper side. We have anomalies, we have a trend here. Maybe that's a contextual anomaly there. We have global anomalies here. Then we have most of the data that is on there. If we were to draw a straight line, we close most of the data points at this level. Also, we are able, on this tab here, we are able to plot the daily mean from the daily mean of the data point. So today, the data is in, we are having a 3.12 meters. This was the May 25, we are getting 2.7, 2.8, and all that. So that is our dashboard here. We're able to plot the daily mean and also get the data from the sensor. Also, the data analysis here, now on the machine learning part, mostly is the anomaly detection. As we were told by Tom during the summer school, is that sensors deployed in the environment, tested tasked with environmental focusing, that is deployment in the environment. They are prone to breakage and damage here. Then we have, so the probability of erroneous readings is quite high, and data corruption also is quite high. So you must employ anomaly detection so that it can get rid of the anomaly, so that you can remain with a clean data set, if I may call it that. Now, our sources of anomalies in this case, the first source is the power supply. I think when I was deploying it, I was a little bit overconfident with my power supply in this case. So because in the day, I'm able to get very, very clear, maybe you might call exact data or very correct data from the sensor. But in the night, the data is a little bit off and it is garbage, if I may say so. So I was a little bit, and I didn't want a system where it only works at night. So I was a little bit overconfident with the power source in this case, because my prototype here is battery powered and it is charged by a solar panel. So I'm looking into other ways of powering or looking into the power source here. So is it a matter of increasing the battery size in this case, or increase the solar panel size? But in that, it will have an effect on the overall design. So I'm looking into that also. So you have the environmental conditions here. Now, the environmental condition is also tied to the power source. So, but you cannot do anything on the environment. Environment is the environment, is how it is. So we cannot do anything to alter what is going on. It is rainy, it is rainy. It is sunlight, it's sunlight. We can't do anything to alter that. So it is quite tied to the power source here. So it is quite tied to the power source. So what we can alter is the power source here, so that we can optimize our power. So that is what we are looking at. Also, another source of anomalies is the network failure. Maybe I say in an ideal situation, in my situation, I'm handling everything. That is setting up the network, setting up the prototype here, data collection, and monitoring the network here. So in an ideal situation, maybe we'll have people tackling the network, we have people being concerned with the software, we have people tackling the hardware part, but that is an ideal situation. But what I'm doing to solve the network failure is that recently a company that is Liquid Telecom rolled out the Sigfox network. So in this area of the network, I'm looking forward into transferring everything I have into the Sigfox network, so that I can, which is loaded, and our budget conservancy is covered by the network. So instead of setting up my own roller network, I can migrate to the Sigfox here. Also on the network failure, Alpageta, the tech lab there has been very helpful. It has helped me monitor keep the network afloat. In this case, they have been very helpful to us, so that to maintain the network and to keep it running. So what we are doing currently we are running, we have different methods of anomaly detection here. So from a high and very generic way, I can say we have 3 methods. So we have predictive confidence approach. This is where you are able to build a prediction model where, so you are able to build a prediction model that depends on the historical data, and the data to train a model, historical data to train a model. And this model can predict the value of the next measurement. And if the value that is gotten from the sensor is very far from the predicted value, then it is regarded as anomalous in this case. So what I'm running on the dashboard there that I've just shown you is the clustering based on supervised approach. So currently I'm running k-means to cluster the data, and the cluster with the highest number of values, that is the cluster we want. Then we dispose of the other clusters now. So the clusters here, the clustering based method is unsupervised. It's just that the data is classified, is clustered into different clusters. As if a value is very far from the centroid of the main clusters here, then it is regarded as anomalous in this case. That is the clustering based and supervised approach here. So this is what I'm running currently. And if I was to just share a snapshot of that, I can come here. I just set up this because of the presentation. So we can take like yesterday, that was 31st. Now this is running it is clustered, then it is plotted as the daily mean. We have 3.18 meters. Then we have, you cluster, these are the values in the main cluster here. But if you come to the real-time data, on the 31st here, you can see there are anomalies which were far off. Then we have anomaly here, which is also far off, but you have the data points here. So these anomalies are scrapped off, and we remain with the main cluster there. So if I was to run that again here, so you can see that the data that is here, that is the anomalies, are scrapped off, and you are able to compute the mean of these data points here. That is the one that you want in this case. So yeah, this was just an illustration of what I was talking about, in that you have a global anomaly here, or a spike. Then after you run the k-means, you cluster the data, you're able to scrap off on this side. So also another method of anomaly detection, that is the statistical profiling, in that you are able to come up with a statistical profile of the data. Then with that, you're able to get rid of the anomalies by just studying the statistical profile of the data in this case. So what I'm also looking into development of a prediction. I'm looking into the predictive confidence approach here, but currently I'm learning the k-means on the clustering, and also I'm looking into the statistical profiling approach in this case. The plan, that is the near future now, is the expansion. After I'm convinced that our system will work, that is expansion to cover other river sections, like I showed you on the map. That is deploying of the water level system pieces, and also development of the water flow rate data, and also maybe to add the water turbidity data in this case. Also prediction models to tackle the anomalies, and also to prediction models to predict the parameters. That is in the works, that is works now in the near future. Also, another one is to incorporation of other data sets. For example, currently we were able to gain rights to access the thermal weather data in this case. So currently I'm looking into the relationship between the shortwave radiation data from thermal, the number of accurate points in a day. So this is data received from, this is 23rd to 26th of May. As you can see, we had very little anomalies in this case, maybe during the early in the morning, late in the evening, maybe one or two during the day. So this was 23rd to 26th. Then this is 23rd to that was 23rd to 26th May. I'm sorry, this should be July here. Sorry for that. This is July, yeah, should be July. Sorry for this, yeah. So the difference between these and this is that there was a lot of sunlight during these days, and there was little sunlight during these days. So you can see the effect. That's why I was talking about looking into my power issue. There was a little sunlight during these days, and there was a lot of sunlight during these days. So we are looking into a way to explain that, and also looking into our power issue also. So this is 20. If you pick a day from this, like now, from here we can pick 25th. You can see that 25th there was a perfect dome of the shortwave radiation. That's maybe you can say the amount of sunlight received during the day. You can see it started at around 6. It ended at around 6 in the other day. So it was a perfect dome in this case. So that's why the data points were quite perfect, maybe in this case. But you can take a look at 25th July. If we take a look at 25th July in this case, here, this 25th July, then you look at its dome here, the shortwave radiation from thermal, you can notice that there are sudden drops. Maybe the system did get to charge quite well. So there are sudden drops and sudden peaks in this case. Also, you can look in July 23rd. It's quite rugged. In this case, it's not perfect. And July 23rd, in this case, you can check out the kind of data we were receiving during July 23rd. So that's why we are employing anomaly detection, and also we are looking into further research into our power issue. Also, another data set we are looking into include is, I talked about the satellite data, that is the GIS kind of stuff, the satellite data, in that to evaluate the amount of encroachment in the catchment, and also the amount of deforestation, the effects of climate change into the environment, so that we can compare with the kind of data we are getting from our sensors, in this case along the river. So because if the land along the river is bare, then there is rainfall, you expect the levels of water in the river to rise suddenly, maybe in an hour or half an hour, because of the amount of runoff, because the runoff is quite heavy. It is not, it's not affected by the vegetation, but if the catchment is protected and there is a lot of vegetation along the river, then you expect the water level to rise maybe in 4-5 hours after heavy rains also. That is another aspect of the project we are looking at. Then our long-term vision, this is like when you are a kid and you are asked what you want to be in future. This is our long-term vision here, is creator of inundation models. Now, inundation models are used to predict floods in a river basin. Now, our project conservancy happens to be in the river basin of Ewasonyiro River, like I just talked about. And we are looking into creation of inundation models. This was in inspiration from a project, a pilot project by Google AI staff from, I think, Israel, Tel Aviv. They were able to develop inundation model to predict flooding in the river basin or in the partner region in India. So that is where we drew our inspiration from. And the main inputs of an inundation model is the water level data, and also the high resolution elevation maps. That these are depth maps of the river basin and terrain, so that with the inundation model, you can be able to predict, maybe when there is flooding, you're able to predict the safe regions, in this case, where the water will reach, maybe in the conditions of during flooding. So you're able to develop safe maps. These are elevation maps, safe. You are able to develop safe maps with safe regions where there are no flooding, and so you are able to evacuate people maybe in good time before the flood sets in. This is where so I've talked about the inspiration, this by Google AI team from Israel here. So my work on water level data may be the first key step to development of the inundation models in this case. So this is an image of an inundation model, how it works. This, I got it from their Google AI website here. when they were on their Google site, where they had explained the whole process of development of the inundation models in this case. Also, that is I call it the end of my presentation. You can check out the project blog post here by Shira Minor from Center for Data Science and AI, that is Dedan Kimathi University. So thanks, and thanks Billy for the controls.
Thank you. Thanks, Jason.
Okay.
We have questions already lined up for you.
Okay.
You may have already answered some. So the first comes from Seku. What tends to be the latency between data collection and storage in the database?
The latency. What tends to be the latency between the data collection?
So if I understand it correctly, so you're using a LoRaWAN based chip.
Yeah. Yeah.
And then this sends data periodically over the network to the server. How long? What's the travel time for that?
Or the travel time is quite limited. It is instant. Maybe it will take a couple of seconds to register on because on the GCP we are running an influx database in this case. So it takes seconds to register. In that, when a data point there is a data that is sent by the sensor from the sensor to the gateway to the network, then it is instant. So it doesn't take a lot of time to register on the influx database, time series database in this case. So it is quite fast indeed, if I may say so.
The next question, which is related to that, is what's the interval between samples and what determines this interval value?
The interval between the data points, right?
Yes.
So the interval between the data points is 30 minutes. What determines it is that we coded it into the multi-tech M.dot, the roller chip, the roller1 chip. In this case, we had coded it into it in that it collects data and an interval of 30 minutes. So to save on power, because we don't need to send at maybe 1 minute, that is oversampling. Even 30 minutes itself, we noted it is because we are dealing with water in a river here. So 30 minutes can also be oversampling, if I may say so, but we coded it to send data every 30 minutes, and we are looking into extend that interval maybe into 1.5 hours or 2 hours, because we noted also that 30 minutes is also oversampling in this case.
Cool, thank you. And third question, which is in 4 parts from Benson, says, since you have a time series, can you use LSTM to detect anomalies? LSTM, long short
term
memory, which is a neural network architecture. Current.
The long short term method here, it's you can use it because it is a deep learning based algorithm, so you can use it to detect anomalies, maybe to classify it as I talked about the predictive confidence approach here. So I think the LSTM here can lie in the predictive confidence approach here. So it can be used, and also other methods, the ARIMA and also the SARIMA, and all that can be used to detect anomalies here. In the preliminary experiment, I was using a predictive model created by Facebook. That is I just wanted to see how it would work. In my case, I used the FB Prophet, the Facebook Prophet, if you have heard about it, which is at its core, it's a regression model. So I was using to detect the anomalies, that I was getting quite good results from it. So that is in my preliminary experiment, but the LSTM can also be used in this case.
There are 3 other parts to that question, so I'm just going to read them all and then you can answer them together. So the first part is, might your system also work for the Nile? In bracket, there are many issues about this water. And following that, might you be able to send measurements using SMS so over GSM technology? And the last part is, are there any methods to reduce energy usage instead of increasing the energy collected.
Okay, so let me start with the Nile issue. So yeah, this is a system that can be deployed in any water body in this case. So you can collect it in other, we can do it in other rivers in this case, that maybe where you think there are floods in this case, you want to monitor the water level, and also in areas where the river is very critical to the survival maybe of animals or people, you can use the system to monitor the water level here and also the water flow rate. Also, the other issue is on the power, other ways of dealing with the power issue. Maybe, yeah, there is other ways, but in this case, what I can see is if you increase the size of the battery, in this case, you maybe end up compromising the size of design. And when it comes to IoT deployments, I think the size of the whole design matters, because you don't want quite a large design so it becomes a problem during deployment. So the size matters also. So other power, currently, the only maybe viable method is solar power. And solar power now, it depends on the amount of sunlight you get in this case. So I will look more into that in the power issue also. But it is quite a hectic field to deal with, because you don't have to, you're not powering the device from the grid. So it's quite a hectic field to deal with, but I'll look into it. There was another question, Billy, I didn't get it. The sent, maybe the second one.
Yeah, so that's the question was, can you also send the measurements by SMS?
Or via GSM. Now that is a whole different architecture now. In this case, we are using the roller. Now I've not looked into the GSM method of sending, but I'm confident it is possible to send the water level through GSM. If it is possible to send, yeah, and also because GSM, there are also different IoT networks. I talked about Sigfox, where you are able to, Sigfox from Liquid Telecom, that is a company operating in Africa. They managed to roll out their IoT network, Sigfox. So on my part, I talked about the problems I'm facing with the network. So instead of concentrating more on the network, I can concentrate on other issues concerning the project. So I'm looking into migrating into that, but also GSM can be explored to send the data packets in this case.
Thank you.
Yeah.
All right, so we'll move on to the next speaker.
Okay, I see engineer has raised a hand.
Oh yes, engineer. Okay, engineer, last question.
Hello, good morning. Thanks, Jason, for very exciting work that you're doing with Sheila there. Yeah, so just a few questions on my side. So one, you mentioned that you are looking at extending the network. So do you have an idea how many more sensors would you need to deploy onto the river? I think you said that's River Ewasonyilo.
Yeah.
To have a desired or an optimal monitoring density. And then the second question is more on the usage. So the models and the data that you're collecting, is this being used?
Yeah.
Thank you.
Okay, now because it is a work in progress, we have not come up with a figure on how many sensors we are able to deploy along the river, but we have not. So it is a work in progress. So we need to maybe conduct more research on the environment where we are able to deploy it. Maybe and also it will depend on the section, on the areas that are suitable to, maybe if I may use that word, suitable to deploy the sensor. So we have not come up with a figure yet, and at this point I can't tell you how many sensors that we can deploy along the river so that we can meet a favorite maybe deployment density in this case. So we have not come up with a figure yet, but it will take maybe a reconnaissance visit to the whole length of the river. So so to mark up points where, suitable points where we can maybe deploy the sensors. Also, I think your second question is on the state of the art. Maybe it's the same system being used to collect data from other water level bodies. Maybe what I've read on is there are different projects that have been done, but not on the rivers mostly, but on artificial, maybe reservoirs, water tanks, and all that. Those are water tanks, reservoirs, dams, maybe around Kenya and also around the world. They have been able to deploy water level sensors to sense the water level fluctuations, maybe. Yeah.
So my question was more on whether like the conservation department is actually using the information. If you could comment on that. And then also just to say that perhaps you could obviously reach out to, I can put in touch with my team here.
Okay.
We've been doing a lot of optimization in terms of the power usage. And so being able to run a solar unit 24/7, I think we've been able to achieve that to some extent. So you could reach out to myself. I can have some discussion on that.
Yeah, thank you very much for that, engineer. Yeah, because I talked about the tech lab at Olpajeta Conservancy. They are very, very inquisitive with what we are doing there, because they are looking into ways where we can give them, I remember when we had a talk with them, they were asking us to give them a figure maybe every week or every day, a figure that can explain the water level every week, every day. So they are very inquisitive about the area of research we are conducting. And also I think my colleague talked about on Thursday, that is Jared. He's also a colleague at DSAIL. He's also conducting his project there on classification of wildlife animals here. So the tech lab there has been quite supportive, and also the management there is quite inquisitive about what we are doing. So because the river is a very critical, maybe critical area, because it is the only river that goes through the conservancy, and it is dependent on by a lot of wildlife. So the whole management is quite inquisitive with what we are doing there. Thank you, engineer.
Thank you, Jason.
Okay, thank you, Billy.
Nice. We are going to move on to the next presentation from Andrew Liakimuzi. Andrew, you can present whenever you're ready. And this is going to be on food insecurity again.
Thank you very much. I'm very happy to be sharing my work in this forum. I'm called James Andrew. I'm a PhD student from Mbara University of Science and Technology. My PhD is on developing better models to track food scarcity from web and phone data. What I'm presenting today are part of the results that we have generated for this research. Coming to the presentation, polarity and similarity measures towards classifying an article on food insecurity. We are proposing that polarity and similarity measures are potential features in predicting whether an article is on food insecurity or is on something else. Why take an old route? This is what I mean. Machine learning currently can generate features automatically. What we are proposing, we are generating these features manually. Here is the issue. As data scientists, you can easily identify unique features which are different from those ones that are generated by machine learning. What does it mean? We have an opportunity to combine these two features. Perhaps we can have a better prediction. Justifications for the features selected. We are going to begin with polarity. Imagine I have two sets of articles, one on food insecurity. I'll be using the word food insecurity and food scarcity interchangeably. I have one set of articles on food scarcity and another set of articles on something else. These articles here, which are on food scarcity, will have tendencies of negative polarity. Now, when you come to these ones on something else, they are going to have both negative tendencies of polarity as well as positive tendencies of polarity. We have a problem. It looks polarity is not a good discriminator because we thought negative tendencies could help us tell that articles which are on food insecurity are negatively, they have negative polarity. And yet here we are also having those ones which are also have negative tendencies. So what do? This is what we suggested. We said we are going to take a risk. Let's ignore that limitation and we see what's going to happen. Suppose it doesn't work. We can always come back and try to see how we can go around the situation. Next, I'm going to take you through how we are measuring polarities for these articles. This is a code which is measured of a text. The polarity it gives is between -1 and +1. I'm proposing some positive text. So it is giving us 0.7 and the message is positive. I'm requesting the online community to send me a 2-word text which is super negative so that we try it. Moderator. Hello, moderator. Moderator?
Yes, I sent a word, bad day.
Bad day. It's giving us negative. So we can use this one to have some confidence. Now this brings me to the articles. We used a scripper tool to download the necessary articles. We script this tool from one of the news media in my country, Uganda. Here are the articles that were retrieved. As you can see, for each article, we are grabbing the date when the article was posted, the title, the content. Now, when it comes to label, the label. These labels were manually generated. You read through an article. If it's not on food scarcity, we're giving it 1. Something else, we give it a 0. Let's go back to the Python. Here, we have pandas. To load the file. Thank you for that lecture on Python. We used up popularity. Now on the other X, we have a section for polarity. Doesn't seem to fit. We are applying on each of these articles to generate different polarities. Now,
we seem to
the
be
next
losing you
thing
there.
was to compute polarities. I beg your pardon? Hello? Can you get me?
We seem to be losing you there. Maybe if you stop the video, it will be the latency.
Okay, let me stop. Okay, let me just stop it.
And then share the screen again. Thank you. We're back.
Okay, applying different articles. And squeeze all the articles. As I've shown, the text is much bigger. So this one are small. The average polarity class 1. Class 2. We also call polarity
We lost you again. Can you share the screen again?
This is what 1,000. The reason multiplying by a small decimal values. Let us look. We see the average polarity for those ones others is 65 0.6, and many others. This one is also 68.
Andrew?
What does it mean?
Sorry, Andrew, can you share the screen again? Oh, we lost him completely now.
Perhaps you could, if you could send the presentation to you, you could show it and move it as it.
Andrew, we lost you there. Can you try it one more or send me the presentation and I can share it from here?
Okay. What about is more in
Since we are having real troubles getting through to Andrew.
Oh, sorry, I can't share my screen.
Try it now again. Yeah, your internet seems to be really bad, dropping in and out. Okay, now we can see you. Go ahead.
Okay. I have stopped where we are able to get average polarity for class 0, that is articles on something else, then average polarity for class 1, that is for articles on food scarcity. So we can see there is some discrimination. Much as it's not good, but let's see what is going to happen. Now we come to similarity. With similarity, if you have some articles in one bundle that are in class 1, food scarcity, and you have other in class on food. But if you measure what we did, We generated a chunk of text. This is the chunk of text which is on food scarcity. Now we measured the similarity between this text and any other articles, whether in class 1 or in class 2. I'm going to generate an article, a text which is on food scarcity, and try to see what similarity does it generate between the message and the text we have proposed. By the way, as you go through the text, it is talking about food scarcity, ending hunger. So let me just enter the text. So we can have some positive similarity. The other text, some online community nothing to do with food. Moderator, hello?
Hello, you're really breaking off.
You've not got?
Yeah, maybe
I will press.
Can you email me the presentation and then, or
I'm about to finish.
Okay, then just finish.
Okay, I'm suggesting some text here. So the similarity is 0. So what we did, we generated polarity measure, similarity measure between these articles and generated similarity scores. We went ahead to compute the averages. As you can see, the average scores, they have a good discrimination gap. That means this is a good discriminator. Now we went ahead to these features to be better than exciting. We went ahead to generate a graphical presentation. The gray labels represent food scarcity. The rest is in dark. Still, we can see that there is some level of discrimination using these features. Conclusion and future work. The study has demonstrated that polarity and similarity measures are useful in classifying if an article is on food insecurity or not. To improve performance, future work considers 1. Revisiting and tuning the previous steps. Lastly, blending this strategy with automatically generated features. Thank you.
Thank you, Andrew. Any questions? I know the presentation was breaking in and out. We will be sharing the notebook and the slides on our repository for those who want to go through it again one more time. Okay. Are there any questions at this time? We're going to have just 2 more presentations before we can take a break. If there are no questions, we'll move to the next talk, the talk from Colleen.
Hello. I'm going to be talking about geometry and topology and epidemic tracking. I'm hoping that my connection holds on. We're having a hurricane here, so apologies in advance for anything kind of weird happening during this. I had been involved in the response of Mali's Ministry of Health in the 2014 Ebola outbreak, and some of the methods that I had used during this project kind of led me to wonder if there were better ways to approach predicting and tracking epidemics than what was out there. In particular, after 2014, there have been some new developments in differential geometry and differential topology that have been applied to time series data. And during the 2018 Ebola outbreak in North Kivu, I was called in to do some work on some of the time series data coming out of different provinces. And I thought that this would be a good opportunity to kind of explore these methods a little bit more in depth to see if these were viable for predicting the spread of outbreaks. The data that I used is open source, so if anyone wants to kind of play around with these methods, it's on the Humanitarian Data Exchange, which is a great place to get data. To evaluate the efficacy of these methods that I was exploring, the time series data was split into a training set and a test set, using the first couple of months as the training set and comparing the results that I got from these algorithms to the January and February data. So with the time series clustering, we wanted to kind of understand some of the transition points. So epidemics can have some of these spikes or exponential growth. They can slow down considerably or have kind of constant growth. And there are a couple methods in topology that are really useful in clustering data. So there's a tool called Morse-Smalley clustering that's had some success in analyzing financial time series data. Basically, thinking back to calculus, this method really looks at first and second derivatives to be able to partition data. So you can kind of think of like water flowing from the top of a mountain to different valleys and kind of being able to map out the mountain based on where the water is flowing. You can also do this with functions on a manifold and be able to kind of partition things out into sources and sinks within that manifold by identifying these minima, maxima, and some of these saddle points in the level set. And by partitioning this, we can get different clusters. There are implementations in both R and Python. So if you want to play around with these methods and get a little more familiar, there are open source implementations. I had also wanted to kind of look at travel networks and some of the newer tools in network analysis to understand some of these case gradients along travel networks. So in an epidemic, you have people traveling from one region to another. If we think about the COVID epidemic, international flights that are bringing an epidemic from one region into a new region, I had wanted to look at identifying regions at risk using some of these network-based models, and also identify some areas that were showing improvement to understand the growth dynamics of the system and which areas might be impacted next. One of the main limitations of the more traditional epidemic tracking methods and other time series methods is really the limited time frame. So a lot of them don't work, several months out or several time periods out, whatever time periods you're looking at. And I thought that taking this network approach might be able to provide a little bit more time to be able to prepare and get resources in place. So a little bit of background on this method. There's a tool called Foreman-Ricci curvature, which basically is looking at how much stuff is kind of weighing down your network based on information spread. It's been used a few times on social and biological networks to understand the structure of networks and kind of where some of the important connections and changes over time occur. And we do this by looking at the different edges. So looking at connections between towns, hopefully you guys can see this all right. You look at the connections between towns 1 and 4. The edge has a value of 4. But if we look at town 3, that's connected to town 4 and town 2, there's a total of 18 on these edges, which kind of pulls things towards town 3 on this network. And that's basically what this curvature measure is looking at. And by looking at changes in this over time and how the edge weights are changing, which in the case of travel networks is either differences in cases or differences in the flow between towns, how many people are going from point A to point B in the time period, we can understand how much this is changing. And so we applied this over the first couple of months of the epidemic as a proof of concept and used it to forecast regions most likely to be impacted in later months. And this is something with this algorithm here and taking the difference of edges over multiple time periods, you can generate custom code using the iGraph package in either R or Python. Once we had this proof of concept and were able to validate that these methods were actually able to find some of these things in the data and forecast out for a couple of months, we were able to let the NGOs know which regions were most likely to be impacted for the resources to be positioned quickly. Unfortunately, right after this analysis, there were some issues with violence against healthcare workers in a few of the regions that were being impacted, particularly stemming from some trust issues in rural areas. There's a lot more work to be done in validating this approach with respect to epidemic trends, but the proof of concept has given us a good starting point in investigating how these tools might be able to help in future epidemics. Right now, we're looking at a little bit of the COVID data to kind of see if this method might work with that type of epidemic where things spread a lot more rapidly than Ebola. And that's something that hopefully there are some results in the next coming months. Any questions? I'll be around on here for a little bit to answer questions, and if you want to connect with me on LinkedIn or send a question via email, please feel free to do so, especially if you're interested in applying some of these methods or investigating them.
Thank you, Elaine.
Any questions?
Fantastic. So looking at the Q&A, there's already 2 questions lined up. So the first is, in time series data, there are rules of thumb about when to use cumulative versus incidence numbers. No, are there rules of thumb about when to use cumulative versus incidence numbers?
So there are a couple different approaches that you can use with time series. I had used both cumulative and incidence. Cumulative can be helpful if you're looking for kind of the volume of the epidemic. So if you're looking at total population impacted over time. Incidence is usually better if you're trying to understand rates of change. So if you start seeing spikes, you'll get the exponential kind of trend in your graph. For a lot of these analyses, we went with the incidence rate rather than the cumulative rate.
Mm-hmm. And the second part of that question, I'm assuming that answered your question, Sekou. The second part is, there are differences in the way you calibrate modes which integrate networks and epidemiology models.
Yeah, so each method really has different ways of calibrating. Especially within epidemics, it's usually related to forecasting. So you can take percentage that you're off in a time period and look at that. With the networks, it's a little bit harder to benchmark that. We had just taken a proof of concept of if the regions that we had identified as future hotspots actually became hotspots. I haven't seen a lot of work with calibrating these type of network models. It's a relatively new tool, and it's mostly been compared to other types of graph metrics. So there are different importance scores, and it's mainly been used in that. Does that answer your question?
I think so, Sekou. Does that answer you? He says yes. Any other questions? While people are still typing, I have a question. So in the graph that you showed, so that's an undirected graph, right? So so the emphasis on the edges. My question is, how can you bring in directional information to this? Based on the equation that you showed, that's a formulation for undirected models. But what if I have a fully directed, or at least partly directed, if I know a little bit the direction of spread of something from epidemiology, for example?
Yeah, so there's a more complicated formula than the one that I showed, but the math has been worked out for that, and you can definitely apply these methods to directed graphs. It's just a little bit more complicated and usually split into pieces where you kind of have one direction and then you have the other direction as a different graph.
Nice, thanks. Any other questions? I guess there's no other questions. If there's any more questions, just put them in the chat. Colleen is still here, can answer them in the meantime. Otherwise, let's move to one more presentation before we take a break. Thank you, Colleen. So the next presentation is going to be from Megan.
Yes. Hello, everyone.
Hello. So Megan's going to tell us about optimal decision-making in healthcare. Taking off from what we just heard from Colleen.
Yeah, perfect start.
Right, you should be able to present now.
Okay. All right. Hi, everyone. Thanks for being here today. I know that we're getting close to a break, so hang in there, and hopefully we'll be able to talk through some interesting topics about optimal decision-making in healthcare. So my name is Megan Allen. I work for Inspired Ideas, which is a small tech startup in Tanzania. And we're super passionate about how we can build digital tools that machine learning and other emerging technologies to help people and improve their lives. We've focused pretty specifically on the field of healthcare by deploying intelligent tools to lower cadre healthcare providers, such as people who work in dispensaries in rural villages, to improve health decision-making as well as improve health outcomes. Ideally, that's what we'd like to be able to do. Just to kind of qualify myself a little bit, I am not a data scientist by training, although we pretty consistently use data science in our work and in my daily life now. In fact, I'm a biologist and global health specialist, and I'm just super excited about using technology and how it can have an impact on the field of health. So I pretty much lie at the intersection of how we use technology and also make sure that it's exactly useful for the specific problem that we're trying to solve, which is why I'm here to talk to you about that today. So yeah, today I'd like to talk a little bit more about optimal decision-making in healthcare using machine learning, and specifically to explore how machine learning can, or what machine learning can offer healthcare providers in terms of decision support, and how we can make sure that we're leveraging the various achievements in machine learning technology to actually augment decision-making in an effective and useful sort of way. So we're going to go on a bit of a journey about decision-making to do that. Okay, so we're going to step back a little bit and kind of talk about what decisions are from a more general perspective. You all already know this, although you might not have been thinking about it very specifically, but decisions are something that we are making all of the time. They're conclusions or resolutions that we reach after some amount of consideration for something. All of you have made at least one decision today, which is to join this presentation and maybe listen to me. But during this process of deciding whether or not you were going to join, you had to weigh a set of options to sacrifice something potentially in order to be here versus be doing something else. In order to make that decision, you looked for various evidence, or you maybe made a calculated risk for how you were going to spend your time. You might have looked at the title of this talk or of the title of other people's talks and compared it with trending titles on Netflix, let's say. Maybe you thought you would learn something new, or that you could maybe just watch Netflix later. So what your decision was ultimately that you would be here sitting with us and enjoying these conversations today. And I'm glad you did that. I'm glad we're here together. So ultimately, this is to point out that we make decisions all of the time, and decision-making is actually not that easy of a process. We do it pretty regularly, but it's a pretty complex process, and we don't really know that much about, we know a lot, neuroscience has come a long way, but there are some things that we don't entirely know about how decisions are fully made, which is really interesting. And particularly a key point I think we'll bring up later on in the talk as well is that the more and more decisions we make throughout our day, our capacity to be able to make high quality decisions often gets reduced. So fatigue gets higher as we move on throughout the day. And sometimes the decisions we make now are not the decisions we would make if we were in a different context, or if we knew different information, or if we had more experience. And all of that will kind of come back around to why it's important for healthcare specifically. Okay, we're gonna walk through a short decision-making process to explain some of these ideas. So let's take an example of a sport in Iceland. This sport is called flonkerton. You can see here the name. This sport is a sport where teams have to wear these snowshoes, these weird snowshoes, and they have to do an obstacle course and go around this mountainous terrain while carrying a camel to get to the finish line. Okay, so I'm sure none of you have ever heard of this sport before. That's probably because I made it up. But I'm going to ask you a question now. I'm going to have you make a decision related to this sport. And the question I'm going to ask you is, there are two teams, Team A and Team B, and I want you to make a bet on which team is going to win. Based on all of the information you know right now, just take a quick second in your mind and you can think which team is going to win, Team A or Team B. All right, now, what if, now I'm gonna tell you a few things about the teams. So Team A has a bunch of players that look like this kind of strong, strong sort of look. They've been doing a lot of push-ups. Team B has a bunch of players that maybe haven't been doing a lot of push-ups and sitting on the couch like I have the past 3 months. So now you know a little bit more information. Which team are you gonna bet on? You can just think about it in your head. All right, but what if I told you that I'm gonna give Team B rocket ships or rockets or some sort of device on their snowshoes to make them go faster? Now, which team are you going to bet on? What if I told you that Team A has won 8 of the last 10 matches that they've participated in? So I hope you're starting to see that the decisions change on the basis of new information and new evidence that gets presented to us. In the absence of any new evidence, so at the very beginning, your decision likely wouldn't have changed from just a guess, just a random guess, and it would have been just that. And your guess maybe would have had some sort of bias or previous assumption based on something that you knew. Maybe you thought Team A is better than Team B, right? But otherwise, you really have no idea about how these decisions are made, and you likely have a high level of uncertainty about the decision that you're making. Which brings us to an important point about the role of uncertainty in decision making. There are so many things that affect our decision making. Like I said, they're complex, and naturally there is uncertainty, or there are things that we don't know in every decision that's made, no matter what, right? Even if we know, even if we think we know all of the things, there's always still assumptions that have to be made. So, you know, as more evidence was presented in the sports example, the certainty that you were making the right decision might have increased with more evidence. But there's still uncertainty even at the end, because we don't know anything about this sport. And we also don't know about the weather in Iceland today, right? Or what's happening in the global market, right? There's so many factors that could affect this. There's still high levels of uncertainty. And one thing about uncertainty, which is going to play into some of the conversations about how we make optimal decision making in healthcare, uncertainty is really mentally demanding. It requires that we weigh all of the options, that we generate conclusions based pretty much only on what we know, and that in real life decisions, we're bringing all of our prior knowledge and experience into the situation, which affects our own levels of uncertainty. So even me as an individual, I might have a different level of certainty about a situation than, say, you, Billy, because we know different things and we have different experiences. So this will prove to be really important for optimal decision making. There's just no way that you can make an optimal decision without knowing what you don't know. And ultimately, we should make decisions making sure that we're choosing ones that we're most certain about, but also knowing to what extent we are uncertain about the decisions we're making is really important. So let's go in a little bit towards decision making specifically in healthcare. This talk isn't about obviously just about making decisions, but it's about understanding and considering decision making in healthcare specifically, and how we might start to consider ways to use data science and machine learning to support these decisions. In medicine, making good decisions is a lot of what doctors and clinicians are doing on an everyday basis. Doctors need to accurately diagnose disease and determine the best treatment strategy among different possibilities for a specific patient in that specific time. They are obviously trained as experts in this regard. They go to school for a long time to learn how bodies and diseases work, and they train for years to understand the process for making these decisions. And they also have access to a bunch of resources to help them do that. And they do a pretty good job at it, given the situation. But now there are a number of challenges that clinicians and doctors face when making decisions. Some of these can, of course, depend on the type of patient sitting in front of you. Oftentimes doctors make decisions based on limited evidence. They might not know everything that there is to know about the patient, right? High uncertainty. They might have limited knowledge. So this is something that we work on in Tanzania with our health projects, is that we focus specifically on healthcare providers who might not have access to training materials, or might not have been or received 5 years of medical training, for example. So, if they're operating from a place of limited knowledge, that could affect their decision making. They might have limited investigative tools or diagnostic decision support tools or tests. I know that in many of the rural dispensaries where we deploy some of our work, they don't have any diagnostic tests. They can't run blood samples. They can't determine what sort of bacteria is making people to be sick, etc. Let me just close that. Okay. And these challenges have real implications and consequences for both clinicians and patients. If a diagnosis isn't made properly, for example, for whatever reason, the patient can be misdiagnosed and given the wrong medication. And this has really serious implications. If the healthcare provider doesn't have the knowledge or the skills needed to make a diagnosis, this risk of misdiagnosing is sometimes quite high. A study done in Tanzania in 2016 noted that nurses, particularly in rural dispensaries, only diagnose patients correctly about 37% of the time. And in the US, it's estimated that 5% of US adults seeking healthcare advice are subject to diagnostic error. So we expect these to be higher in places with limited resources, and we have to really understand the implications that poor decision-making can have on patients and doctors. So this might pose an opportunity for innovations using machine learning to support decision-making in healthcare. As machine learning technologies have become more advanced, as all of you know, more capable, more reliable, there's been a surge in the application of machine learning in the health sector. And while machine learning itself isn't necessarily a silver bullet, there have been significant advances in these types of approaches. Since this is the work we focus on here at Inspired Ideas in Tanzania, and given that many of you are likely interested in ways that data science can be used to solve problems and help make decisions, I want to look briefly at some of the opportunities that exist for supporting decision-making in healthcare and machine learning. So like I said, machine learning technologies, of course, have the potential to transform the way that healthcare is delivered and received. Even Colleen, your example of how you can use some of these methods for helping understand disease outbreaks and be able to provide that information in real time to NGOs is incredibly helpful and useful for planning and for resource allocation and things like that. It's important to note that a lot of the solutions that are currently being developed and used for health applications are often considered narrow AI solutions. This just means that they're specific solutions to very specific kind of problems. So for example, machine learning is used in healthcare to identify abnormalities on lung X-ray images, such as this one here, to identify possible drug candidates for diseases, to detect diabetic retinopathy, using images captured by mobile phones to classify patients as high risk for developing congestive heart failure, et cetera, et cetera. Of course, there are many other examples that I'm sure you're familiar with. And in many cases, these applications of machine learning and AI perform as well as highly skilled clinicians and doctors. It's, you know, in the literature, and they're definitely, these approaches are in some ways at least meeting or overachieving what a doctor is able to do in terms of decision making. In the case of images, for example, machine learning algorithms can see that the things that the human eye might not be able to see. They're quite good at exploring large amounts of complex data that the human brain can't comprehend all at the same time. And they can do things like offer prioritized directions, meaning that they can guide health decision making and help reduce decision fatigue, which we talked about before, that could impact the brain's decision making process. So while these applications are awesome in their own right, and all of you, I think, you know, if you're a machine learning practitioner or a data scientist, you've either worked on or heard about some of these types of solutions, and they're fantastic. It's some of the stuff I started out working on as well. But we have to question whether or not these are enough to radically change healthcare in the way that they're promised. So this is something we started asking ourselves at Inspired Ideas. We wanted to know and to explore ways that machine learning could not just make good decisions, but could actually support clinicians in making better decisions holistically. And it turns out there might be a lot to consider here. So, you know, first, current algorithms often don't supply clinicians with an explanation of why it decided to make a certain decision. And we'll talk about why that might be important shortly. A model might be great at identifying patients who are at high risk for heart failure, but might not be able to easily explain why they think this patient will experience heart failure, just that it will. And so this, you know, there's some challenges here that are very specific to healthcare, as well as for machine learning applications more generally. But of course, if we want to actually be able to provide supportive decision-making tools that optimize health decision-making at a holistic sort of level, we have to start thinking about how we can take these really targeted, narrow machine learning approaches and start to generalize them a little bit more, or at least as much as we can. Or how can we utilize other sorts of methods that allow us to be able to dig into the explainability or the interpretability of these models. All right, so how might we start thinking about optimal decision-making in healthcare using machine learning, and what are the things that we should consider? In order to do this, I want to walk through a couple of scenarios with you, so hang in there with me. These will hopefully be interesting. All right, so quickly, we have a couple of scenarios. The first one is Lucy's Clinic. Lucy's Clinic is located in a rural village in Arusha, Tanzania, not far from where I'm currently standing, actually. The clinic is made up of 2 rooms. Lucy herself, who is a clinical officer, but not a 5-year school-going clinician, a nurse who does triaging and administers vaccines, and a small pharmacy that can dispense basic drugs. All right, she's trained in diagnosing and treating many common illnesses and has experience treating patients in this location for 10 years. To make better decisions, she relies mostly on her previous training and experience, and sometimes relies on books or guidelines that have been given to her by the Ministry of Health. Sometimes she's uncertain about her decisions, so she tries to run diagnostic tests, but her facility doesn't have a lab, so this is actually quite difficult for her. Despite her training and her experience, she's not a specialist, and she did not attend, 5 years of medical school in this case. One other challenge that Lucy faces is that she's never heard of conjunctivitis. This is a disease, an eye disease. And so since she's never heard of this disease, it is actually impossible for her to make a decision or a diagnosis about this disease and treat it. Lucy's also subject to her biases, which we all are, but she definitely is, which may or may not be incorrect. So for example, after diagnosing 8 patients with malaria in one day, she's likely to make a diagnosis of malaria again because she's already seen so many cases of that disease, even if the patient only has 1 or 2 symptoms that might indicate malaria. One great thing about Lucy is her interaction with patients. So she has a lot of prior knowledge of the patients she sees, and she's able to read subtle signs and clues, right? As humans, we're able to do that quite well. So for example, Lucy sees a patient who has stomach pain. She asks the patient a bunch of questions. She rules out food poisoning or other stomach conditions. And then she remembers that this patient had challenges related to domestic violence, let's say, in her home. So Lucy starts asking questions about this. She remembers a few studies also about stomach pain being related to cervical cancer, but she has to admit that she can't remember everything that she read, of course. So ultimately, she decides to refer her patient to another facility for further testing because she feels like she can't make the final decision there. Now, all of this is just an explanation of a typical day in the life at Lucy's clinic and serves as an example of the decision-making process of a healthcare provider, although this is not exhaustive of the process, and the challenges that she sometimes faces in making those decisions. Keep these challenges, I think, in mind as we explore the next one. So now let's imagine a separate clinic with exactly the same circumstances as the clinic we just saw, except in this case, the clinic is entirely run by an AI, quote unquote. This clinic is really crazy. It's really something else. From state-of-the-art cameras that can detect if someone has jaundice or is different color, to human pose estimation algorithms that can identify if someone has a limp. All of the sensors and algorithms humanity can legally build have been assembled into now what is called the Clinic E42-22. So the AI that sees patients here is trained on a massive data set of patient records, covering a vast range of possible symptoms, their corresponding diagnoses. Contrasting to training of a new clinician, it only took a few hours, maybe to a few days, to train this AI doctor, as opposed to 5 years of medical school after 15 years of regular education. Decision-making is a very straightforward process in this clinic. The patient provides the inputs to the models, and the model crunches the numbers and produces an output. After a while, the numbers indicate an improvement in health outcomes, which is a good thing. Now, could all of this be true? Let's see. We know that the data used to train the algorithm was collected locally, in Tanzania, for example, which is good. But we also notice a staggering number of diagnoses in the data set that could only have been made with certainty if the data collectors had access to expensive equipment, which we know they did not. We take note of this and chalk it up to uncertainty in the data set. Next, we look past diagnoses and decisions made by the model for past cases. We then notice that the decision makes sense, but we're unable to ask more questions because the deployed models are state-of-the-art, complicated neural networks. Well, maybe that's what it takes for high accuracy, but in this case, didn't give us a lot of opportunity to ask questions to the model. We also notice an overall decline in the number of patients who are treated, and after conversations with villagers, it became clear why this is true. The villagers feel not cared for at the facility and even doubt the decisions made by the AI, saying it doesn't even ask me how I'm feeling, or I miss when Lucy would help me through some of my personal problems. Now, just to note, there's some exaggerations here, obviously, but maybe you can kind of see what a clinic would be like if it was just being operated by AI. All right, our final scenario, I promise. So for this final scenario, I want to take us into the future a little bit. And it's a future that we're currently working on here at Inspired Ideas. So I'm going to build on the previous two scenarios to start having us understand how healthcare providers and machine learning technologies can work together for optimal decision making. We're going into the future because this is the vision we have for how AI tools can be truly supportive. So this clinic here, Lucy Plus AI, it needs a fancier name, but Lucy Plus AI is powered by a dynamic duo. The healthcare worker is the final decision maker in this case, but the AI is her loyal sidekick. A patient walks into the clinic and is joyfully welcomed by Lucy and invited to take a seat. Lucy does a quick scan for new bruises on the patient's body, because this is the same patient as before. And because of that, she suspected domestic abuse, since last time the patient was here with her husband and there was some problems related to that. There are none this time. Lucy asks the patients a few questions to understand the context of her situation and records this information in a patient file that the AI is diligently watching. As she adds more information, both her and the AI are updating their beliefs on what the true underlying cause is. Lucy has exhausted her list of questions she had, in addition to proper history taking. So she decides to turn to her sidekick, the AI, and see if the AI has anything extra to add. The AI recommends a few more questions to ask because it had some additional connections that were made that Lucy had not made. And the responses are recorded, and a probability distribution over diseases is presented to Lucy on a screen. Lucy scans this list of diseases and closely investigates the top 3 diagnosis options. Especially, she pays attention to the uncertainties presented by the algorithms. And it turns out she had come to a different conclusion than what the AI had come to. So in order to get some clarity, she taps on one of the diagnosis options on the screen, and she taps a button that says why, which the AI then goes and presents to Lucy the process at which it took in order to derive this conclusion. While it's a compelling argument, Lucy has to manage her own uncertainties. So she goes back and does the same thing for the various other diseases that are offered. There's also an opportunity for her to ask why not one of the solutions, especially the one she's thinking about in her head. And she then receives a counterfactual argument for why this might not be the best decision. In this case, Lucy ends up going with her gut and disregards the AI's top diagnosis anyways, but she was able to explore more options in a shorter amount of time and manage her own uncertainties. Here, in our future AI Lucy clinic, the AI is empowering the healthcare worker to explore a multi-dimensional space easily and identify possible avenues to explore. It's able to hear reasoning for why and why not decisions are made, which are crucial for optimal decision-making. Now, this is our take for how optimal decision-making happens inside of healthcare, using machine learning and AI particularly. And what we really hope to be able to do, and kind of the main point of what we're trying to share today, is that machine learning tools should be deployed in order to support the decision-making process, not make the decisions on their own. So let's just run through the qualities that we went through them in a scenario sort of version, but now let's talk about these qualities actually, right? Qualities that make optimized decision support tools, and that we can actually start to integrate and think about how we can integrate in the machine learning approaches that we're using. So the first one is that it takes into account uncertainties, which I think at this point we've talked a lot about, and hopefully you can see why that might be important. Another good quality of a decision support tool is that it's explainable. So in this case, that the doctor can probe the model, like Lucy could ask the model to help her understand what the decision-making process was. It's important for the model to be interpretable by healthcare providers and stakeholders, both at Lucy's level as well as at various other levels. And this interpretability has to be intuitive, right? If we output a bunch of results that actually aren't understandable by the clinician who's actually using the tool, then the tool is useless for that clinician, right? So it takes more work and it takes a lot of time to understand what makes something interpretable to someone. And this is obviously quite subjective, but it's a really important thing to try to understand how to make sure that we can optimize decision-making using interpretability. Another key feature is an ability to iteratively update to include new information and examples. So this is something that humans do kind of naturally by reading or learning new things or getting access to new information. We need to have models that can be able to do that really effectively, right? We want to be able to quickly make updates based on new information that we see, and not have to spend a lot of time, retraining models, for instance. The last two are that the tool is able to ask questions that challenge is a strong word, but that go beyond the scope of the healthcare provider's knowledge base, right? So if we can ask questions outside of that knowledge base because of the information that the machine knows and can understand, then we have a better chance of optimizing the decisions that are finally made. And lastly, transparency of the models is important for auditing purposes. Just really quickly, this list is by no means exhaustive. So there might be other things that you can think of, and we'd love to hear about them and talk to them. And it obviously depends a little bit on the context in which healthcare tools are being deployed, as well as the scope of the problem that they're trying to solve. So yeah, if you have any more, feel free to chat them, or you can email me at the end. There'll be an option for that as well. And I believe that these are iterative processes that likely we won't get right all of the time, and we won't get right away, right? There's been a focus on understanding how we can make machine learning models more accurate to achieve the same level of decision making as healthcare providers. So that, there's an obvious first step there that's needed. So now this process, and there's an opportunity for us to take this process further over time and be able to transform our mindset for how we can actually integrate decision-making tools into the healthcare workflow. And I think if we're really vigilant, particularly by we, I mean builders of tools, developers, stewards of data, if we're really vigilant about building tools that are capable of empowering healthcare providers, we'll actually be able to see the radical transformation that's promised by AI in healthcare. All right, yeah, just a couple of kind of final decisions. So just a couple of considerations based on our scenarios. The first is that Bayesian modeling and probabilistic programming is a great way to achieve the qualities of an optimal decision support tool, like we've been talking about. The second consideration is that the interface matters. So we can build incredible models that outperform doctors at every single turn, but if there's not a clear, simple way for the clinician to interact with these models and for the decision-making to be built into the healthcare workflow, then the use of machine learning models for optimized decision-making will be useless. So as we saw in the scenario, Lucy's able to easily and simply, in an ideal world, interact with the models and be able to gain value from them for her decision-making process. The fact that this doesn't happen very seamlessly right now is a criticism of many machine learning tools for healthcare today. And there are lots of ways that we could help support this. There are other interfacing methods we could use, such as sound and voice, that could be deployed to help be able to take in information, natural language information from a patient visit, for example, and then be able to kind of record all of that information and help make decisions and inference based on that. That's something that we're currently working on here at Inspired Ideas, and we're super excited to be able to test it out a little bit in some of the locations where we're working. And the final thing is that accuracy is important, and I don't want, there'll be some diehards here who really want to make sure that the accuracy is high and that the models are reliable, and I also want that to be true. But I think it's not the only thing to consider. Measures of accuracy and precision like UAC and ROC curves, F1 score, information criteria, etc., they can be helpful depending on the scenario in which they're used, and should be used to gauge how well models are performing. But we don't have to necessarily, I'm saying this with a grain of salt, we don't have to necessarily sacrifice accuracy and reliability to build transparent and interpretable models. And I would argue that the transparency and the interpretability and the explainability outweighs the high accuracies that could be, achieved by some types of machine learning tools. All right, so let's consider that we're making better decisions, in the healthcare in the healthcare clinic. And I just want to point out a couple of the decisions that then happen kind of beyond the clinic in this case. So, if we're using these sorts of tools, ideally we're able to optimize decision making at the first point of care, which could have a number of benefits, right? We could see increased health outcomes. We could see better allocation of resources. We could see more accurate diagnosing and treatment of patients, et cetera. And so one of the questions becomes then, and something we've had to face, is how do the optimized decisions at a rural clinic where we're deploying our machine learning models make a difference as we move up to a regional or national scale? There's not a clear answer to some of these questions, but I think it's something that we have to consider, especially when, if at a rural clinic we're making better diagnostic decisions, for example, and we're able to see when and where and why a disease might spread to other locations. This then has an impact on whether or not resources are allocated differently across the country or to various places. It has a difference on whether or not these diseases, if we can prevent them soon enough, whether or not they will actually spread. And it makes a difference for how, one interesting thing we've seen is that it makes a difference for how particularly antibiotics are prescribed. And so antibiotic resistance is a really clear challenge, particularly across places in sub-Saharan Africa and Asia. And if we're able to make better decisions in the moment and not diagnose patients unnecessarily and treat them unnecessarily with antibiotics, then we're actually able to change the resource allocation of those antibiotics and potentially impact the future of antibiotic resistance spreading across the country. I think another thing to just consider really quickly is that all of these qualities of good decision support tools have to be considered across the spectrum of decision making. And here it says interpretability across the spectrum of decision making, but really all of these qualities are important. The reason why I'm pointing out interpretability is that there are almost always multiple actors that are responsible for making health decisions. No one works in a silo or by themselves. And as we move around the spectrum of decision making, so from a rural dispensary to a specialist clinician at a hospital to someone who works in the Ministry of Health, we see that the results and the outputs of the models that we have to be different. So for example, this might mean that we, at one level, we have an output of a model of a probability of 0.8 that a patient has malaria with an uncertainty of 0.5, let's say. We might have to change that for someone who works in a rural clinic to a statement, to a more interpretable statement, something that says, we think it is most probable that the patient has malaria and we're only about 50% sure of that decision, right? So changing it from kind of numerical outputs to written outputs that help be able to interpret what it is that the model is saying. And I think this is one of the big challenges that we face, because a lot of the people that we're dealing with who are starting to utilize these machine learning models aren't actually trained in data science or to understand how to read some of the outputs that are provided. So it takes more work, 100% it takes more work to be able to understand what that looks like, but I think it's a really important point to at least make, and a consideration that should be utilized when we're making these machine learning models, particularly that will be deployed in specific types of settings. My final slide, and just a few thoughts that I want to point out as additional caveats. First, I talked a lot about the importance of interpretable models, right? That's been kind of my whole argument, is that we should make models that are interpretable and explainable. But it's not just enough, actually, for models to be interpretable. It's a great first step, but interpretability, and one of the reasons I'm saying this is because these words have been thrown out kind of a lot recently, especially in the data science and kind of machine learning spheres. But it's not enough to just be interpretable, right? We can say our models are interpretable, but that doesn't necessarily reduce the biases that models might have, and it doesn't make decisions fair. So this conversation is probably a whole another talk on its own, but just know that traditional machine learning models often learn things like gender or racial biases that can undermine their effectiveness when used in a healthcare setting. And we have to make sure that we're able to build models that produce fair results without unwanted biases in order to optimize for decision making. So there's a lot of considerations to have here. Second, just because the model is interpretable doesn't mean that we should make it accountable for decisions. Ultimately, decision making still lies with the healthcare provider, in this case that we're trying to build. And I think it's an important point that is stressed kind of in scenario 3, the scenario we talked about, that the purpose of building probabilistic machine learning tools for healthcare providers is to support their decision making and not to make decisions for them. And there's a really fine line here, I think, but we have to make sure that we're both making this clear to the people who are using the tools and that we are avoiding healthcare providers shifting accountability to the tools unnecessarily or entirely. And this isn't just because I myself or we as developers and data scientists want to avoid blame, right? I don't want to necessarily be blamed, but I don't want to avoid it either. It's just because the power of humans and AI together in healthcare decision making is better than just one of those making decisions alone. And ultimately, we want to keep that power in the hands of the healthcare providers who are really there to serve the patients that they see. And my last point here is actually kind of the same as the one I made before. We obviously want to make models that work and work well given the information that they have. Doctors also want this. It's something that they of course tell us and that we read about, that doctors want models to be accurate and reliable. But there's been research to show that we can get similar accuracies using interpretable machines, with the caveat that it's maybe a lot more work, but we can do it. It's not easy, don't get me wrong, but it is possible to be able to have machines that are interpretable and do a good job of actually supporting and optimizing the decisions of healthcare providers. And I think that's all I have to say. I'm happy to answer any questions, of course, and yeah, feel free to connect with me on Twitter or LinkedIn, and I will put my email in the chat, so you can feel free to email me if you would like. And thanks for your time.
All right, question time. Oh, I think there's already questions in the Q&A. Okay, so the question number 0 is, are there ways the students can or have been able to explore research in the context of your work?
Yeah, good question. Absolutely, there are ways to kind of use the work that we've done to help students with research, or to help researchers with research. We have a couple of examples of this that are currently happening. One is that we have a number of machine learning and / data science master's students and actually undergrad students who have come to work with us on solving specific kind of challenges using the frameworks that we're deploying in healthcare settings. One of those, for example, is to build some models around predicting whether or not a patient will adhere to their antiretroviral treatment if they're HIV positive, and trying to help understand what are the factors that really make a difference in trying to determine whether or not a patient will or will not adhere. And we have some other research work that we're currently in the process of doing, both around HIV care and building interpretable models for HIV care, as well as for pediatrics and pediatric care delivery. So absolutely, there's a number of ways students can explore research in the context of our work. And I'm happy to share my email. I was like, what is that called? My email with you guys, so that you can feel free to send me a message if that's something you'd like to consider.
All right, and the second question, still from Psycho, is, so in you had a list of qualities of an optimized decision support tool. The question is this something that you've published and thus we can cite?
Yeah, really good question. So it's not something that we've currently published, although we're in the process of putting together a paper and ideally being able to publish it out of some of our work we did last year in northern Tanzania, specifically related to pediatric care. We deployed our tools across a range of healthcare providers and tried to really understand how these various qualities are making a difference in the terms of their decision making. So again, that's something that I could share out with you, and hopefully it will be published one day soon. And Saku or anyone else, if you're really interested in this, I'm happy to chat with you kind of offline about how we could get you more information about the different qualities that we're using and how we're describing them.
All right, and the last question from Psycho is it's hard to develop interfaces that users find intuitive. Are there any suggestions you have on how to do this across a broad range of users?
Yeah, this is a really good point, and I think it's taken us a long time to to get to the point we are, and still a lot is needed to understand how to really build intuitive interfaces that are useful. And so I think, you know, in terms of building across a range of stakeholders, we've really had to, I think the main suggestion we've had is to sit down with people at the stakeholder level that you're trying to build for, and then really understand what it is that their needs are and understand what the workflow is that they're currently going through. So one thing that we notice and that we love to do as developers of technology is to build tools how we think that they'll be used, right? And how we think is most useful. And for example, we took some of the tools that we had. We have an interface where people can interact with some of our models on a tablet. And so we took that to a clinic, and then we kind of just observed over the course of a couple of days. And when we came back, you know, they weren't really using it in the way that we thought that they would. They were recording some data in it, and sometimes using the inferences or the predictions we were coming up with, but weren't necessarily using it all of the time in kind of the dedicated way that we had proposed. So, you know, we had to realize that the healthcare workflow is, one, very different across a range of contexts, and is also very static in how in a single context. It's very static in meaning that it doesn't change very easily. So us trying to take technology to a rural clinic in Tanzania to improve health outcomes poses some challenges when the clinic is not necessarily prepared to integrate that technology into their workflow. So I think the major points is just to understand what is needed and how it can be introduced, and then also start to think outside of the box. Like I said, if, you know, we're under the impression that if we can build different interfaces for different stakeholders that optimize kind of their workflow and their decision making, that actually the tools will be more useful for them. And one of the ways we've thought to do that is the voice example that I was sharing with you before, which we think is a really awesome and potentially exciting way to have doctors interface with machine learning models and algorithms through kind of just their natural language. So.
All right. Another question for you is, are you looking at all diseases, or maybe concentrating on certain diseases, e.g. chronic diseases only?
Yeah, good question. So currently we cover around 500 diseases. So we're kind of all over the place in terms of our disease distribution. But we also have different stakeholders who are interested in different things. Naturally, I guess, as a small startup company, we've been able to develop partnerships with people who are interested in HIV research and care provision, as well as pediatrics, as well as non-communicable diseases, et cetera. And across, so not only across a range of diseases, but also across a range of locations where the tool gets deployed. So some of our stakeholders are very interested in deploying in pharmacies, while others might want to build tools that help researchers understand, you know, how we can predict antimicrobial resistance or something like that. Yeah, so I think largely to answer your question, I think, you know, we're covering a lot of diseases. We have a lot of stakeholders, people like MCC, PEPFAR, UNICEF, the Botner Foundation, who are very excited about how we can deploy our tools. And ultimately, we want to be able to cover as many diseases as possible, because it helps us build a holistic sort of tool that ideally covers as many gaps as we can.
Good. There are more questions coming in. So it's a question from Francis, which says, what surprised you the most in your work in terms of context in the work with the rural Africa, and how are you going to make the platform sustainable?
Yeah, good question, Francis. It's been a great and interesting learning experience. I think there are two things that have surprised me the most. The first is that technology penetration is quite high, and much higher than I think we had originally expected it to be. The technology and mobile phone penetration in Tanzania particularly is rising at a pretty steady and very quick rate. And so that's been cool to be able to kind of leverage those advances to help, people be able to access these sorts of tools even in rural places. And I think the second thing that surprised me is people's interest and willingness to try to understand what we do. There's obviously in some places, there's a gap in understanding, okay, this is what artificial intelligence is, and this is how it can make a difference, and this is what it can really offer me. But I think that anytime we've gone to kind of rural clinics and tried to describe what it is that we wanted to do and show them, people have been very receptive, which was really cool. And they've been really honest and open about whether or not the tool or the various features were going to be useful. And while that sometimes sucks from a development perspective, it's really good if our mission is actually to build something that makes a difference for people. So those two things for sure have surprised me, and it's been a really fun and awesome pleasure to be able to continue to do this work. And in terms of sustainability, it's a question for the ages, Francis. I think we, right now we're, like we said, we have a number of partners and various stakeholders who are interested in kind of specific solutions or specific sets of diseases or something like that. So ideally we'll be able to continue to research and develop alongside them and have their support in doing that. Moving forward, I think ideal would be being uptaken by the government, which we've heard is a difficult challenge. So if any of you know how to do that, please let me know. But ideally we'd be able to have some sort of sustainability plan that includes financing that could help support a rollout across the entire country of Tanzania, across the entire region of East Africa, right? Wherever it is that our tools and solutions are needed, ideally we'd be able to go to those places. So anyways, continuously exploring that all the time.
Any more questions?
I was just looking at the chat. I just wanted to give a shout out to Sekou, who said there are no winners when moving a camel. And you are very right about that. So I'll let them know in Iceland that they shouldn't play Flonkerton anymore.
I guess I have one question, which is sort of meta, which is, so what's the baseline for this? So if you're going to talk to something, let's say a policy person, like a minister of health, and kind of pitching this. So the status quo is, if there's not enough people to make decisions about diagnosis, for example, the status quo is just hire more doctors or train more doctors. So I guess when do you know that this has succeeded? What's the baseline? Performance or something like that? Yeah.
So the like measuring of the health outcomes is the ultimate like measure of performance or of success, I think. So we're kind of in the process of currently doing some studies and have plans to do some in the future to better understand specifically how these tools can improve health outcomes specifically. So there's a measure of whether or not they improve just decision making or the perception of decision making, but then on a broader scale, we have to really understand, like, okay, well, if they are making better decisions, does that mean people are getting healthier? Right, and that's really one of the big value propositions that we've been able to discuss with people, with policymakers or with various stakeholders, to say, if it is true that these types of tools can actually increase health outcomes or improve them in some sort of way, or help companies or nonprofit organizations or countries as a whole move towards some of the larger international goals for health, then that stands as a solid ground, at least for us to be able to start testing and see if the tools work, as well as to be able to define like measures of success for that. So.
Cool. Any final question before we break? I guess there are no more questions. So that's it. We're going to take a short break. We'll be back at 12:30 Kampala time.